back. I hope you had a good night's sleep. So today I'll talk about the anatomy of slowly slipping faults on continental settings. Of course, all this work, which is there's a bit of an overview at the beginning, and then there's some things that we did with a lot of people, including all of these people here. Some of them are in the room, and they will recognize themselves, and I thank them warmly. Yeah, thank you. So, I start just with this picture. You're probably aware of this, and so we'll go really quickly over this. Plate boundary faults, or faults in general, accommodate the displacement between two blocks, the relative displacement between two blocks. Most of the time, these faults are locked, and these blocks are moving at millimeters per year. They accumulate this elastic strain energy within the crust, and once some threshold is reached, the fault will slip rapidly. We're talking about meters per second, and this very rapid slip will lead to the radiation of seismic waves within the crust, and these are the seismic waves that we fear during earthquakes. So this is the classic view of the elastic rebound as formulated as early as the early 20th century. A little bit more recently, but not that recently, we start to see mentions of something called a seismic deformation in the literature. As a result, it has been identified what is now called a seismic slip, which is basically the same thing, just slip on the fault, but occurring over a very long time. And some of them actually slip continuously over decades to centuries. And we're talking about millimeters per year of slip. Some historical papers. One of the first mentions where there is actually a quantification of a seismic slip is the Steinbrügge 1960 paper, where Steinbrügge and his colleagues went to the cellar of a vineyard in California. The people realized that actually the walls of the cellar, which was newly redone, were being cracked because the concrete slabs of the floor were being offsetted. And the offset was consistent with motion of the San Andreas fault, and they were recording no earthquakes at the time. And so they produced a first measure of time-dependent evolution of creep. Intriguingly, they fit it with a linear model, and they conclude that the fault slips at, I think at this place it was something like 1 centimeter per year, something like that. And they mention in the paper that a fuller knowledge of fault creep will lead to an important modification of Riet's theory. So it's really a new they're opening a new era in seismology by saying, like, well, you know, faults, they can release strain by sliding slowly. That's not me. No, okay. Sorry. Since then, a lot of people have been working, and actually slow slip has been discovered on many faults across the world. And although this is completely unverifiable, I am tempted to say that the more we look, the more creeping sections we will find. In red, you have all the subduction zones with identified variations of coupling or presence of a seismic slip that have been identified globally. I mean about geodetic evidence, and maybe some of them are missing. And the green dots are all faults along which we have discovered a seismic slip by different methods, be it creep meters, INSAR, GNSS, etc. So this map is evolving constantly, as many people publishing different stuff. And of course, the historical measurements were made along the San Andreas fault, but about 10 years later, there's a paper by Niklas Ambrazés on the North Anatolian fault, which is also quite an important one. So, why am I not working on subduction zones? That's one of the questions. Subduction zones, we reached a point where we have now a very nice description, a phenomenological description of what happens in subduction zones. They're going fast, the fault is going fast, there's lots of earthquakes, lots of big earthquakes, they're frequent, They're dangerous as well. There's lots of different phenomena, slow slip events, VLFEs, etc., etc. Lots of variabilities in slip mode, and we learn a lot. Okay. My problem with subduction zones is that you're always very far from the megathrust, and you need to actually put instruments on the seafloor, which is extremely expensive, in order to reach the megathrust and be as close as possible to the megathrust. And so probably one of the questions is that the very small scale of processes is very difficult to reach. So of course, there's some papers that are contradicting me these days that are coming out, where we start to see very, very fine scale of subduction megathrust structure thanks to seismology. But if we can put our fingers on the fault, I expect that we will be able to find a very small scale description of events. So today I will show you a brief summary and some figures, some data. How does it look like in the data, this seismic slip? So that's the first thing we'll do. And then I'll show you a lot of data that we have collected on the North Anatolian fault over the years. There's no real interpretation. It's not really finished work. So you'll have the privilege of seeing these data first. But there is no real interpretation. So if you like models, you might be a bit frustrated. And I'll try to finish with one potential explanation for some of the faults, the creeping faults. Why are they creeping? I try to put out a tentative model to explain why they are creeping. And so I'll talk mostly about the San Andreas fault, the North Anatolian fault, the Chaman fault, the El Pilar fault, and the Hairen fault, and the Leyte fault here. So it's kind of a world tour of creeping faults. How does a creeping fault look like from space? So of course, when you talk about creeping faults, you really, really want to go to California and see the one that has been most studied in the past. I can't cite all the papers that have been published on the San Andreas creeping fault. It turns out that there is several sections when we're talking about creeping faults in California. So this is an INSAR velocity map that has been derived from Sentinel products by Xu et al. 2021 from San Diego. The color from red to blue is line of sight measurement. So line of sight measurement is this weird measurement, but basically what matters in INSAR is the gradient of displacement. Okay, INSAR is very good at measuring gradients. And so all you care about is gradients, and you can see that you have this block in red moving in one direction, while that block in blue is moving in the other direction. And when you go across the faults, which are marked by these dark lines, you can see a gradient of color across that. When this gradient is gradual, it means that you're accumulating elastic strain within the crust. Okay? While when the gradient is extremely sharp, it means that the fault slips at the surface. So we can identify some of these creeping faults over almost the entire figure here. You have the Hayward fault right there, the Calaveras-Paicines fault, which creeps a little bit right there. Of course, the San Andreas fault creeping section with Parkfield somewhere here. This part is creeping quite rapidly right here. Then you have this entire section that ruptured during the 1857 Fort Terran earthquake, which is locked, seemingly. And then you have some evidences of creep on the San Andreas fault system near the Salton Trough. It's a little bit harder to see around this region because INSAR is a little bit more difficult to do because of agriculture right there. But basically you see creep all along the fault in various places. This is a subsidence signal related to hydrology in the Central Valley, so nothing to do with creep, although it's the highest, by far the largest signal. Another fault that we don't really talk very often, but actually produced very, very, very nice set of data, is this El Pilar fault in Venezuela. It's the southern part, the southern plate boundary of the Caribbean plate, and it crosses north of Venezuela. And actually, when you do an INSAR velocity map, so this is line of sight in radians per year. So This is our little INSAR trick to make us look smart, but actually it's not very complicated. With these data, one radian is about it's ALOS data, so it's about 20 centimeters for one cycle, and you have to multiply by the line of sight and divide by 4 pi to get everything into distances per year. Whatever. You once again see one block moving in a direction, the other block moving in the other direction, an extremely sharp gradient, really, really nicely outlined here, which follows exactly the surface trace of the El Pilar fault. And here it's a little bit looser, and then you get it back right here, very sharp, and then there's a bit of noise around here. That's typical INSAR velocity map you can get. Of course, there's some creeping faults in Tibet with that many strike-slip faults over an entire region. Some of them are creeping. Here it's the example of the Xianshuige fault by Xiao et al. In 2021. There's been a flock of papers on the Xianshuige fault over the recent years. And they're somehow all consistent to first order. Once again, this block moving in a direction, this block moving in a direction, and a very sharp gradient across the fault right there. Here the authors were nice enough to convert in millimeters per year. And we're talking about, you see, 4 millimeters per year in the direction of the line of sight. Okay, so direction of the line of sight is something like this. So now, and same thing for INSAR. For those who do not know INSAR, remember that what we measure is the scalar product of the displacement in 3D with the line of sight, which is a unit vector. All right, next. One of my favorites, because it's also one of the longest, and there's very few studies on it. This is the Chaman fault. The Chaman fault sits at the boundary between the Indian plate and Eurasia in the Macron. So we're in southeast Pakistan. The north of I think the boundary between Pakistan and Afghanistan is somewhere here. Yeah. So the northern end of the Chaman fault is in Afghanistan. The southern part is in Pakistan, and the city of Chaman is right here. And you can see this very nice gradient, very nice knife cut across the image that you can follow along the fault. You can actually follow it for about 350 kilometers. So it's creeping at a measurable rate for about 350 kilometers. I said that we would look at the very fine scale of a seismic slip, and I'm showing you pictures that are covering entire regions. What matters here is that these maps have been made with pixels of a resolution of several hundred meters. Okay, native resolution of these radar data is pixels of 20 by 5 meters. Over the processing, you arrive at an averaging. You use averaging somehow. And you arrive at final pixels of about several hundred meters, at best 100 meters, sometimes better, but that's this kind of scale that we can reach with INSAR. So I'll try to now take you with one example and how do you go from these surface measurements to whatever happens at depth, and trying to go down scales. So we go to Turkey. North of Turkey, there's this North Anatolian fault, which accommodates the motion of the Anatolia block with respect to Eurasia. The North Anatolian fault is this guy here. It's quite an important fault in terms of seismic hazard because it runs to Istanbul and goes across the Sea of Marmara. And one of the very important results, or at least observation over the last century, is this westward propagation of large earthquakes along the North Anatolian fault. And we see only part of it. 1943, magnitude 7.6 earthquake. 1944, magnitude 7.3 earthquake. 1967, 7.2. 99, Izmit. It doesn't take a genius to say that we are awaiting another earthquake further to the west within the Marmara region. It's probably complicated, but it's really a region at risk right now. The color map behind is an entire velocity map. Since I wanted people to be able to read it, I projected everything, and so I made an assumption saying that there is no vertical deformation, which is probably an assumption, so no vertical deformation, and we are looking at here, assuming everything is horizontal. So it's just a measurable assumption. This here is a region that is creeping along the North Anatolian Fault near the city of İsmet Pasha. I'll talk a lot about İsmet Pasha because it's the historical place where Andreas made his first measurement. And Bayramören, which is the eastern end of there. Mentioning these names because they're really, really tiny villages, but at least they're good landmarks to mark the western edge and the eastern edge of that creeping section. If we remove all traces, we see that line here. You have this very sharp cut across the image. This creeping section extends. So we have GPS stations around here, so it's creeping a little bit around here as well. So from here to here about. And you see that across the fault you have a jump of about up to 1 centimeter per year in full parallel direction. If you overlay the historical rupture traces, one thing that is intriguing is that both the 1943 earthquake, it's a 7.6, sorry, and 1944 earthquake right there, nucleated or started in this region. The only paper I found that actually relocates the epicenter for these earthquakes is this John Dewey 76 paper, and he places the epicenter of both earthquakes in this region. There, he doesn't place them on the fault, on the main North Anatolian fault, but they must be somewhere around here because these guys are very large ones. And it seems like the 1944 earthquake actually powered through the creeping section, while the 43 earthquake went eastward. So they both went in opposite direction. This is what's commonly accepted. I'm not a paleoseismologist and I will not argue about it, but it seems that there is some discussion about the fact that the earthquake actually went through the creeping section and that the ruptures, the surface ruptures that they measured here are actually related to this earthquake or an earthquake that occurred in 51. So it's a bit debated, but I do not wish to go down that route. If you measure slip rate at the surface as a function of longitude around here, you see that basically to the east you see nothing, to the west you see somehow nothing, but it's noisy, and in the middle you have this very nicely shaped creeping section. Creep reaches about 9 millimeters to 10 millimeters per year, and the city of İsmet Pasha, where everybody has been measuring creep in this region for a long time, sits around here, around 6 or 7 millimeters per year. Now, if you take all this, do an inversion, and try to find the best model that actually explains the data at the surface, this is something you can get. Okay, so here we use a Bayesian approach. This is the mean of all the models that fit the data with respect to our prior. If you want details on this, I can talk about it for ages. But the take-home message is this. We have, and I'm overlaying the two ruptures as well here, we have this creeping section. It's pretty small, okay? It's not as large as the San Andreas Fault creeping section here. This is about 50 kilometers from here to here, 50, 60 kilometers. And we have these 44 and 43 earthquake ruptures overlapping on this. The second message is that outside of the creeping section, the locking depth, which is the transition between the surface, the locked portion, and whatever's creeping at depth, whether it be ductile flow or whatever, this locking depth is somewhere between, I'd say, 15 kilometers and 20 kilometers, and I can't really say exactly where it is because it's difficult to constrain from the surface. And that's outside of the creeping section. inside of the creeping section, we see this locking depth that actually comes closer to the surface, and we have this locked region at depth and rapid creep near the surface. So this is basically my own interpretation of whatever happens in this region. You can trust the model a little bit more, a little bit less, but that, I think, is the take-home message for this fault. This is how it slips over a decade. And if you, this thing is going too fast. Yes. If you take two depth-dependent profiles of slip rates normalized by the actual plate motion across the fault, you have this within the creeping section. You have your locking depth, which is somewhere between 7, 10, give or take, considering the uncertainties, and you have rapid creep at the surface and half of the plate rate at the surface, while the other locked portions are basically locked down to 15 kilometers, and then I do not know exactly where the locking depth is. It could be anywhere in between. It could be a gradual transition. That's a question I cannot answer with these data. And so this is basically a summary of this figure. Whoops. Now we go to another fault which has a completely different behavior, at least kinematically speaking. It's the Leyte fault. We're in the Philippines. This is a fault that's accommodating the oblique convergence, the oblique subduction in the Philippines and the east of the Philippines. I wanted to show you this picture because this fault is actually creeping everywhere at a rate of about 35 millimeters per year. Okay, it's just creeping everywhere. When you do the INSAR velocity map, it's just a step function across the island, except from one place, this region here, which is not that big. It's about 40 kilometers long, a little bit less. Doesn't extend very much in depth, about 10 kilometers. And this is actually where we had an earthquake in 2016, magnitude 6.5. There was a previous earthquake about, I don't remember when was it, the first one, the other one. I don't remember. But they're repeating, and they are all of a similar magnitude. But the rest of it is just creeping freely at the plate rate. Okay, that's a kind of another end member. And of course, the San Andreas creeping fault. So that's once again one of the models that have been produced for the San Andreas creeping fault. And the little drawing, the little dashed line which sits behind, is actually consistent with the different published models in the literature. And so, for instance, Jeremy Moore published another one. It's different, but also it's similar. At least the first order is similar, and I think we should consider that first order first. What we see on the San Andreas creeping fault is that you have this fast creeping region in the center, but you also have a little bit of a decrease in creep rate at depth. And same thing, you have this transition between locked and creeping at depth, which is quite deep, where the 1857 earthquake ruptured. Here you have the Parkfield place. Basically, Parkfield happens around here. You have creep at the surface near Parkfield. This is where the 1906 earthquake terminated, and you have this deep locked creeping transition as well. And there is this region where there might have been these foreshocks of the 1857 earthquake. This is same thing. I'm putting a question mark here because these foreshocks are mentioned in some early KRC papers from 78, I think. But clearly the epicentral region of these earthquakes is at least debatable based on testimonies, so it's probably debatable. But there is tiny locked asperities in there, so I don't know, maybe it could work. Now if we go down the scales and try to reach a finer scale than the one I showed you before, which is a general broad view of what we see on the fault, you can use seismology. And so for instance, there's been hundreds of papers on seismology along the San Andreas fault, so I picked a recent one that summarizes lots of things. I think this one summarizes it well. So the black line is a seismic slip at the surface measured from INSAR. The red line is what they call the non-clustered fraction. So it's the fraction of earthquakes, the ratio of earthquakes that they ranked as non-clustered. Okay. So to one member, and the member clustered would be classic sequence of main shock, aftershock, and they're all going together as little clusters of main shock, aftershock. Non-clustered, the other end member would be repeaters that just happen on regular basis, and they do not have aftershock, identified aftershocks at least. And they quantify this fraction, and they say that in the middle of the creeping section, you have a lot of non-clustered earthquakes. So basically, you have repeaters, these earthquakes that are being driven, and their interpretation is that these earthquakes are being driven slowly but constantly by a seismic slip. And on the edges, you have more clustered fraction, and you have this gradual transition from this, this continuous cracking that you hear within the creeping section, and these sequences of clustered earthquakes in there. You also have tremors. They're not on this figure, but they're somewhere around here below Parkfield. They have been detected as well. So earthquakes, repeaters, you have streaks of earthquakes, you have main shock, aftershock sequences, which allow you to actually differentiate different parts of the creeping section. You also have tremors at deeper depth. Now, this is on the fault. This is what's happening on the fault, at least what's interpreted to be happening on the fault. Another question is what happens in the volume. And so there's this very nice figure, very simple, very nice, from this Cheng et al. Paper, NatComs 24, where it's the cumulative density function of earthquakes as a function of distance from the main fault. Okay, so you take all the earthquakes, compute their distance to the main fault, you make a PDF, you integrate it, and you get the CDF. And what it tells you is that if you do that with repeaters only, they all distribute within, well, 90% of them distribute within 500 meters from the main fault. So basically, they are on the fault, right on the fault. But if you take all earthquakes, including earthquakes of magnitude above 1, you actually see that there is actually a significant fraction of them. The CDF is much flatter. There's a significant fraction of them, if we here with 25% of them, which are actually outside of these 0.5 kilometer distance from the fault. So basically, the medium is cracking. Things are happening within the crust around the creeping section. So we're going to actually move across the globe and try to see what's happening along the North Anatolian Fault creeping section. So in black and white, in the background, you have the fault parallel velocity that I was showing with jet awful colors earlier. Creep is here. You can see this knife cut across the image. The green triangles are seismometers. G are geophones. B are broadbands. This one is a station from the Turkish network. It's a broadband as well. These stations, and not the DRS, but all the stations have been installed by my colleagues from GFZ, Patricia Martinez, Dirk Becker, Jorge Jara, etc., with the help of our Turkish colleagues, Ziyadin Sakir, Alpay Özdemir, etc., etc. So lots of people involved in there. The blue rectangles, blue squares, sorry, they're definitely squares, are GNSS data that we have been installing since 2019. And same thing with the help of Zia and Alpay and Ugur Dogan, etc. These ones are also GNSS stations, and I just color-coded them differently because I want to talk about them a little bit near the end of the talk. And this is the city of Ismet Pasha, where a creep meter has been installed since at least the 80s. Okay. If you plot here the national catalog from AFAD in this region, over the time of our experiment, there is no earthquake. There's 0. There's nothing. Okay. So the magnitude of completude is 4. And there is nothing on this map, at least. If you use our data and some smart machine learning things, so I take it that you're now all familiar with machine learning thanks to Quentin. But basically, some of you are probably more aware than me on the method, but they've been using this PhaseNet and etc., then association, then relocation method, and you get something like this. So it's definitely not silent. There is earthquakes. The region that we were looking at in the previous map is this area. Okay, so it's a subset of this. For this map, we're combining our network with stations from the Turkish network. So clearly, this region is not silent. Okay, the biggest ones that you see, these ones, they're magnitude 2s. Okay, so they're small, 2.4, I think. And all these ones are very small. They're 0.5, 0.6, etc., etc. But clearly, it's not silent. The first thing you see is this big cluster of things. This one, you see it in the national catalog. It's the Orta cluster. You have two normal faults here and a little bit of a graben here. We're not going to look at this one. There is also a cluster of events further to the west, outside of this map actually, which belongs to the Goliaca event that occurred in early 2023. So if we take a profile across the fault like this and plot it like this, this is what we have. So this is distance to the fault. This is depth. This is the Orta cluster. So this is normal faulting events, classic ones. And I don't want to talk about these guys, although they are the biggest number. I want to talk about this part here. And actually what's interesting in this part here, so the fault is right there, okay? So I just draw a vertical line. That you have some events that cluster on the fault, and they're actually quite close to the surface. They're right here. But you also have this one, this big cluster of things, which is distributed just north of the fault. You're somehow devoid of earthquakes south of the fault in this region. The first question I was asking myself was like, maybe the fault is dipping. But no, if you consider the scale of things, you would have to have a 45-degree dipping fault here, and clearly you would see that in the geodesy, and we don't. Okay, so the fault is not dipping. At least where strain accumulates does not dip at 45 degrees. So this is not the main fault zone. This is the volume, and it extends over almost 7 kilometers right there. So most earthquakes within the fault zone are actually not on the fault zone in there, and so that's pretty intriguing. If you project all the earthquakes that are within 7 kilometers of the fault plane, and you project them on the fault plane to see what's the spatial relationship with a seismic slip, we actually see something quite intriguing. All of these are the creeping patches, so the two rapidly creeping patches that we identified earlier. This is the shallower locking depth, and this is the locked region. What I see here, and I'm not really quantifying it, but I see that, is that all these events, they fall in between these patches and these three patches somehow. They surround them, and they're not exactly overlapping with them. And actually, I should have shown you this figure. These ones, which are overlapping with this patch, are located really in the volume. They're not on the fault plane. The only ones that are really on the fault plane is this little cluster of guys that happened in April 2023. April 2030 is not done yet. So April 2023. And these guys are also on the fault, and this is actually where the city of Ismet Pasha is. So where most of people have been measuring creep over the past. So we have this mutual exclusion between the occurrences of these earthquakes and the seismic slip that we found. And so one of the things that I wanted to do was to say, well, okay, we have earthquakes. We have more earthquakes where it seems that we have more earthquakes where there is a seismic slip along the fault. And also seems that they're not really, there's some kind of an exclusion between a seismic slip and the earthquakes on the fault. And so one thing I computed was what is the Coulomb stress change? No, the effective stress change. So this is a measure of the shear stressing rates imposed by a seismic slip on the fault and by the deep loading on the fault. So we have tectonic loading, which imposes a certain stressing rate. You have your creeping portion, which also imposes some stressing rates, and the sum of the two is whatever we should observe right here. In black, you have the effect of the tectonic loading, which is at depth. It's really a function between of the distance between the epicenter of these earthquakes and the position of the tip of that deep dislocation. And there is no real relationship between the effective stress at the effective stressing rate, at each of these earthquakes and the density of earthquakes. It's not because you're stressing it more with this dislocation at depth that you will have more or less earthquakes, okay? But if you have the creeping section, if you add on top of this the effect of creep, and that's the red part, total part, you see that you have an excess of earthquakes, so high density of earthquakes corresponds somehow to this higher effective stressing rate. It's not completely crystal clear, but there's still some kind of a slope right there. And so my interpretation here is that you have of course, tectonics is loading the system, but I have the impression that a seismic slip on this fault is actually offloading some of the stress to the medium, which is cracking constantly. So, yeah, right. Now, how much is it cracking? And so we decided to do an old trick, and we just did the Kostrov summation of all these events. So we divided into small blocks. Within these small blocks, we sum the moments of these earthquakes. We divide by the volume, and this is consistent with a strain. We divide by the time, and it's consistent with a strain rate. So what we observe is that and this is the density of earthquake as a function of longitude. There is more earthquakes within the creeping section, and it turns out that they seem to be smaller. Of course, our detection ability is much better within the creeping section because that's where we focused our network. But we do not observe these big earthquakes as we observe right there. And so what I have, my feeling is that, and once again, it's a feeling, it's not really, I'm giving you my first interpretations. My feeling is that we have a region which is off the fault, which has been loaded by, or at least stress has been distributed off the fault by a seismic slip into the medium, and we have more smaller events in this medium outside of the creeping section, and they're bigger elsewhere. Potentially, it could be the signature of some region that's weaker, or some region that's hosting smaller faults everywhere. And if we remember what happened in the past, this is actually where the 44 earthquake powered through, and this is the tip of the 43 earthquake. So maybe one thing that came to my mind is this idea where maybe we're imaging some kind of a region which is weaker because it's been damaged several times over the past. This is difficult to prove, but could be a nice story. All right, how about the time-dependent behavior? How much time do I have left?
13.
13 minutes.
Yeah,
wow.
okay.
Okay. Buckle up. Yeah, we're not going to finish. That's fine. So, of course, these creeping faults have a very nice time-dependent behavior as well. And creep meters have been installed very early. I realized that I should have defined what a creep meter is for those who don't know. A creep meter is a monument installed on each side of the fault, and you measure by any means the displacement of these two monuments with respect to each other to measure slip on the fault. And so the extent of this creep meter varies, the way of measuring varies. Sometimes it's a rod, sometimes it's a line, sometimes it's a laser, it depends. But basically it's the basic measurement is this. And you see, for instance, these creep meters installed along the San Andreas fault, you see that they have a rich temporal behavior. You have seasonal oscillations, you see post-seismic from the Parkfield earthquakes, you see some little transient events happening there. So lots of different things happening on these creep meters. This is an example from an early creep meter that Roger Billum installed after the Superstition Hills earthquake. You see very nicely this post-seismic relaxation along the fault. You also see that this post-seismic relaxation is made by different events. And I think it's Yoshi who published a paper relating the spatial heterogeneity of frictional properties on the fault to actually explain this nice little behavior that we have here. I'll skip on that. Yeah, and one of the things that is intriguing is that we have these. Okay, I'll go this way. Here is a very nice figure, a very nice paper that followed the Loma Prieta earthquake. Loma Prieta earthquake is one of the earthquakes that shook California in 1999. It's a big rupture. It's a 7 point something. And actually what has been observed after some time was that it actually triggered some change in temporal behavior of a seismic slip along the Hayward fault. Okay, so it's distant away from the main rupture. And if you look at the measurement of slip, this fault was creeping before the Loma Prieta earthquake. And for some time, it actually stopped creeping. It's even thought to have been sliding backwards. And after some time, it had to recover. It had this event. Then nothing happens, and then it recovers the slip rate it had before the Loma Prieta earthquake. And so you can see that these creeping faults, they react to stress changes in the medium. So you can make a nice model to explain this, and it works. You also have spontaneous events, and I'm going to jump on this. And you also have, and in order to get a hand on and feel what the amplitude of the perturbation that these creeping faults are reacting to, you have this nice paper from Liu in 2009, where they claim that they see a strain event, so this is strain meters, they see a strain event related to the passage of a typhoon over Taiwan. And just this typhoon, which is supposedly only a change in atmospheric pressure, which we're talking about, we're not talking about megapascals, right? We would have felt it. But we see this strain event, which is related to, which they relate to slip on the fault, and which is supposedly triggered by the passage of a typhoon over there. So we're going back there, going back to Turkey, and we're going to look at these GNSS stations and this place right here. This place right here is actually hosting slow slip events. So this is a slow slip event that we captured using CSK data. It's high resolution INSAR from the Italian Space Agency. This is an interferogram that's been made between August and September 2013. And you see that you have this very sharp knife cut just in 2 months. You have several millimeters of slip within the line of sight. This actually amounts to 2 centimeters of slip at depth along the fault in just about a month. So you have slow slip events in this place. If you look at the creep meter that was installed in the 80s, you actually see jumps, and this place is actually only sliding through slow slip events. This is the creep meter that Roger Billum installed in 2014. For there, it's been offsetted here. For comparison, it's actually still behaving the same, doesn't really change. This creep meter here has been turned on, luckily, in January 23, because there was a data transmission problem before that. And thankfully, we started to have the data coming back at this date. And what we see here is February 6, 2023, which is the day of this huge doublet of earthquakes that ruptured the East Anatolian fault. And so this line marks the day of this doublet. And we see a slip event here and another one right there, okay? Here is the seismicity within our network, okay? So no real big earthquake, maybe a magnitude 2 right there, right when this earthquake happens. This magnitude 2 actually came about an hour after the passage of the surface waves. And if we zoom in on the creep meter, this is what we see. So in red, you have the creep meter measurement. In blue, you have the broadband velocity measurement, normalized and filtered at 0.1 hertz. And in dark, you have the GNSS velocity, because our GNSS are measuring at 5 hertz. And so we have 5 points per second. Okay, let's zoom in on this. If we zoom on this, this is what we see. So this is for the first event. This is the time of arrival of the body waves that we see here on the broadband in blue. And this is actually the time of arrival of the surface wave. The GNSS does not see the body waves because it's not precise enough, but the surface waves are big. They're here. And clearly there's a jump on the creep meter. This jump on the creep meter is of about 20 microns. When I say 0.02 millimeters, nobody's shocked, but when I say 20 microns, people are like, is that true? It turns out, yes. It turns out, yes, it is correct. The creep meter can measure that kind of jump. So this is seemingly correct. Then nothing much happens over about 10 minutes. And then the main creep event starts. This guy starts right there. So you have this delay of 10 minutes. The second packet of waves arrives. This is the arrival of the body waves from the second Karaman-Marsh earthquake, on the Chardek fault. You have the P waves arriving, they're extremely strong, and you have the surface waves arriving, and actually the creep meter also slides and starts sliding for longer, 3 minutes instead of below 1 minute. It slides 10 times more, so 0.2 millimeters instead, so 200 microns instead of 20. And same thing, it stays idle for about 10 minutes, and then the second creep event starts. And it's about 5 times bigger than this one, than the first one, okay? So this is quite a cool observation. What's really nice as well with this is that we have several GNSS surrounding the region. So we don't have just to measure the oscillations. We can also reconstruct the strain tensor every second. And since we have the strain tensor, we can project it and try to intuit or infer the tractions on the fault and the change in tractions along the fault. So we have time series of change in tractions along the fault. I wanted to see whether it was the normal stress or the shear stress that was acting the most on the triggering of this. Frankly, there's no clear answer to this. Basically, things move up and down. Up means opening for the normal stress in blue. Up means opening, down means closing. Positive means tectonic sense of motion. Negative for the shear stress means backwards. I don't see anything clear here, okay? And the same thing for the second earthquake. It's noisier because you're in the coda of the first one, and because our network is elongated along the fault, so it's harder to measure the normal stress right there. But clearly, I believe it's the shaking, and there's no real sense of what happens in there. One thing you can do is go back to these papers about gouge weakening by the passage of seismic waves. This is a paper by Johnson and Xia in I don't remember, 2005, I think. They measured the change in modulus of a gouge by the passage of acoustic waves through the gouge, and they infer a universal threshold of modulus reduction of a granular system that is about 10 to the minus 6. And I was trying to say, well, maybe I have this 10 to the minus 6 thing. So it turns out that when this slip event happens, I have a little bit higher than that, but we're in the same orders of magnitude. And this is actually the same for this guy. What's intriguing with these two creep events is that, okay, they seem to be triggered. There is this 10-minute delay, which might correspond to something that actually reaching the surface and takes a bit of time to reach the surface. But frankly, this one has a higher perturbation and slides very few, while this one has a lower perturbation and slides about 10 times more. So clearly there is something about the behavior here that we could have, and we're basically testing this fault twice. And it's pretty nice. I'm not exactly sure where we're going with this, but we're currently trying to infer if there is a change in the local velocity of seismic waves within the fault zone using our seismic network. There's nothing really obvious currently. We're also trying to find whether there's tremors associated with this. Same thing, nothing really obvious, but that's work in progress. How much time do I have? 1 minute.
No, 2.
2.
Yes. A lot more.
That's not going to happen. Okay, let's go quick then. So I'll go back to my 3 creeping faults, and we'll try to see whether we can find a mechanism. The first thing that I saw in these creeping faults was this. You have some faults with a deep locking depth and no creep at the surface. A shallower locking depth, some seismic slip at the surface, an even shallower locking depth and some slower seismic slip, it's not even locked, and the later fault, which is fully creeping up to the surface. And one point that is important is the position of that locking depth. If you think about it, when locking depth gets shallower, we observe a seismic slip at the surface. That's basically the take-home message from these 3 models that I showed you. Why does it matter? Locking depth actually controls the surface shear stressing rate. So if you have D, your locking depth here, your slip rate at depth, your shear stressing rate at the surface is equal to this. So it's inversely proportional to D. If you decrease D, you increase the shear stressing rate. So basically, if you have, for the exact same amount of time between 2 earthquakes, the shallower the locking depth, the more stressed you are at the surface. So the closer you are to your rupture envelope, the more likely you are to slip. But why slowly? So there are several reasons it could slip slowly. The first one is frictional properties of the fault gouge at the surface. You've heard talks about this. Other mechanism, potential pressure solution creep. Okay, nice. But the thing is that these do not explain the systematic behavior that we see. Why do we see the locking depth going up? Why do we see creep at the surface? Okay, we would have to design a specific ad hoc rheology to get that. And so that's not really satisfying for here. One thing that we could do is we can appeal to pore pressure changes, and I'm going to go really quickly because actually Dimitri Garagash is going to explain everything this afternoon, so stay tuned. At 4, he explains you all these slides through which I am skipping through. Basically, what matters is that with his model, if you assume that there is a flux of volatile going up the fault, you have to have this excess pore pressure at depth to have a pore pressure, effective normal stress profile that looks like this in the end. If you have this type of normal stress profile, your nucleation size at depth, assuming everything is weakening, would look like this. Large nucleation size at depth, low nucleation size within the seismogenic range, and large nucleation size at the surface. And the position of this transition actually depends on the fluid flux. And you can actually modulate the position of this by modulating the flux of fluid going up the fault. So really listen to Dimitri, he's going to explain this. Basically, this is a model that we designed to test this. These faults over there are interseismic distribution, show you the interseismic distribution of slip rate as a function of depth for low fluid flux. Okay, everything is locked. There's a tiny bit of creep at the surface, but it's not fast. And it really looks like these locked faults that I showed you in the beginning. If you start increasing the creep, the fluid flux, then you start to see this creep appearing at the surface because you're bringing up the locking depth shallower, closer to the surface. You're bringing it up even shallower. You have this type of thing where in this one you will even have slow slip events because the region here is too small. And you have this kind of profile, and in the end, when your fluid flux is extremely high, then you have this completely unlocked fault that gives you this. Okay? So, fluids from where? Same thing. You'll talk it out with Dimitri. My take-home message is that I think we find, basically from my side, I think we find a systematic in the distribution of a seismic slip along these faults. Okay? And that's what matters. Then we need to build a model to explain this systematic. And actually, you're going to see it at 4 p.m. All right. Thank you, and sorry for being too long.
Okay. So questions. I know Silva and Roland. So do we have a question from students or postdoc first? Anyone? Just ask one question. Silva, you want to be a student? Okay.
I loved everything you talked about except the last 1 minute. So I find the control of creep by lithology extremely satisfying. In fact, everywhere you look for creep, there is a specific rock there that can explain it. In the Highland fault, it's full of gypsum and it's weak and velocity strengthening. In the San Andreas fault, it's full of serpentinite and at these low temperatures, don't vary serpentinite. And that's also velocity strengthening, like stable. So while I don't refute that there can be fault valving and fluids percolating this, there's this principle of parsimony. You can have a very simple explanation that fits the rocks and the geology and the geophysics and everything. Why look for a more complex model that you can't really
So there's two things. The first thing is there's plenty of places where there's serpentinites and gypsum, notably along the Iron Fault, where there's no creep. So there's also a principle of false positive. And you're like, well, okay, here I find gypsum because I looked for it because there is creep. And actually there is gypsum 25 kilometers west of here, and the Laoshan, and there's no creep. Okay, so where do I stand with this? The second part is this parsimony thing. It depends what you expect by parsimony. I think that a model in which you have, so you'll see is, I didn't describe it, my fault, but you'll see that this model is actually awfully simple, and you don't have to know exactly what the type of rocks you have all along the fault to actually be able to infer the behavior. So, in a sense, rheology and the type of rocks and geology is definitely not simple. That's what I would answer. So, but my main point is that there is weak minerals elsewhere in places where faults are not creeping. And if you look at the San Andreas Fault creeping section as well, yeah, there's serpentinites, but there's no serpentinites next to the Salton Trough. There's here bits and pieces here and there, and it's not actually completely consistent with it. So it works, but not completely. And it does not explain this relationship between locking depth and shallow creep at the surface. Hence, I don't refute that rheology plays a role. Okay, of course, it plays a role. But I think you need something else to explain that weird anvil-shaped creeping distribution of the San Andreas Fault. You needed to explain this shallower locking depth and creep at the surface for the North Anatolian Fault. That's my point.
That was a really fun talk. The most surprising thing and interesting was that hugely different microseismicity on the Ismail-Casa segment, right? No localized seismicity, no streaks, no repeaters, I assume.
No repeaters.
So that really suggests something's really different from all the creeping faults almost elsewhere that we know. What do you think is the factor there?
Well, the short answer is I don't know, but we can elaborate a little bit. So first, there's this model that Yoshi published a few years ago about saying that this fault might be actually long-lived post-seismic, and that would make it very different from the San Andreas fault. I think that after Roger published this paper in 2016, the data evidence for the post-seismic part model is weak, to say the least. So we don't see anymore this logarithmic decay. So it could be something else. Actually, I think it's something else. Now, there's no repeaters yet. We haven't found them. We haven't looked deep enough in the catalog, but they're not obvious. Tremors, I think I see something, but I'm not a good seismologist enough. Before, seriously, when did I think that I was going to make all these presentation? There is clearly a coherent signal that lasts for about half an hour before this creep event that shows up from 3 different seismometers. So there is something happening at depth that might be tremor. And clearly it's not on the fault. Yeah, I don't know. The rheology is not the same, as Sylvain said. That probably matters. It's also a region that has been powered through by earthquakes. So it has a different geological history when we compare with the San Andreas Fault, which we do not have traces of big earthquakes going through. So the medium is probably more damaged, or at least it's different. So, yeah, plenty of reasons.
Yeah, one comment, one question. So the comment I have or question, or sort of question is, have you checked other literature about the threshold of dynamic stresses to trigger?
No. No, I haven't.
Matt Way and I published in 2015, looking at
Okay.
headline landers triggering on creep, based on creep meter observation, creeping
The Superstition Hills Fault?
Yeah, 0.01 millimeter creep threshold. So
Yeah.
what's the level of dynamic stress that is needed? And it's 0.6 MPa, so roughly consistent
Okay.
with the range that you're reporting.
Yeah.
So well, I'm just curious, like how common these thresholds are, and it seems to be consistent from other studies.
Yes. So I checked that. Yeah. You mean from the? Sorry, I thought you were meaning from the experimental part.
No,
But from the data side, yes, it seems like everyone is finding thresholds that are on the order of 0.1, 0.5, 0.6, point something MPa, and below 0.1 we don't see triggering. That's also what I found in the literature. I don't know. Yeah.
Well, the question I have is similar to Sylvain's. Can you elaborate a little bit on the mechanism? Because it seems to me that even if you invoke core pressure changes, from that to slow slip is another extrapolation that one has to make. So it's actually a complex model. It's not,
I think.
To match the transient nature of slow slip, right?
Yeah.
One needs to invoke fairly complex assumptions. And so I wonder, like, following one's point, that the lithology or some other explanation might be more straightforward.
I'm not saying lithology does not explain things. I'm saying lithology does not explain the first order observation that I have, which is this relationship between locking depth and shallow creep, okay? Which I believe is...
Temperature, lithology, temperature,
well,
even stress.
so why would temperature change over 40 kilometers? So, because that creeping section in Turkey is very, very short.
I guess what I'm saying is the frictional property, the effect of frictional properties on lithology, temperature, and pressure.
Okay, I guess my problem is that if you, okay, I'm going to put it bluntly. If you take a brush and some painting and put a dot on the fold, yes, you will have what you're expecting. But it's not very satisfying because we're completely unable to test that. We're never going to be able to dig everywhere and find all the lithologies along all the faults of the world at the scale that apparently matters, which is a very fine scale. As you put it, you said in your model, well, the scale has to be, I mean, if you put things at very small scale, we'll never be able to know that. Now, it doesn't mean that it's not true. I agree. It doesn't mean it's not the controlling factor. Now, if you take some very simple assumptions about the behavior of permeability as a function of effective stress, you can show that the actual normal stress profile looks like this in a fold that is sustaining some fluid moving up, okay? And so if the profile looks like this, then the consequence is that using the classic thermal granite distribution of rheological properties, you have this behavior that emerges. And you don't need to tune it very complicated, in a very complicated way. And in the end, what matters as well is that you can combine that with where are these creeping faults? And where are these creeping faults? They are above subduction zones. They are above a basin gorged with water which is subducting beneath that. So in a sense, of course, you always have possibilities and evidences of fluids. We also know that there is fluids circulating in fault, and we don't really know what the effect is on these first order slip behavior. And so that's where I'm going. It's not really going further than that. Okay.
So can you put your slide with the creep, the Western Turkey, Northern Anatolian? Maybe the one where you have the three,
oh yeah. Okay. I see what you mean. Yeah.
Yeah.
Look.
So the bottom one, the first thing that comes to mind is that there is like deep water coming up and feeding all the way to the surface, like this
Yeah.
Knocking depth and surface creep up. But then if you loop that in, if you have fluid circulation, then you have alteration of rocks.
Yes. Yes.
And therefore you will have
Yes.
ecological response.
Yes.
And so
And the main problem of this is that you have fluids, so you have reactions, so you're generating minerals that, I mean, and this is all loosely and hand wavy, but you will have minerals that are full of fluids, and these minerals are probably weak, and you are probably sustaining a seismic slip. And so in the end, well, yeah, and if you go even further down the line, this fault will never cease to creep, and creep will extend, and in the end, all faults on the planet will be creeping. So yes, there is a problem with that. I agree.
I think
Yeah.
we can leave the discussions later. Maybe Andreas will ask the last question, and then we're going to the next talk. So Celeste, are you here? You can set up the computer, maybe.
So I agree. So you triggered slow slip event by the direct.
Yeah.
Very interesting. Do you have some constraint on the location of the trigger?
Of- On the trigger slow slip, so we're working on it. But with the INSAR, I'm trying to do the time series on my free time. But since the creep meter doesn't show any difference with the other creep events that we had in the past, it really feels like it's the same region. So in short, it's about 1 to 2 kilometers depth over 7 to 10 kilometers lateral extent. So it's small and very shallow.
Three mental cards.
Yeah.
They are sense almost same location.
I would tend to believe so. I'll tell you after we have the. I won't be able to resolve these two events independently, but the sum of the two I'll be able to tell you in hopefully in a few weeks.
Great. Great. Thanks so much for
Thank you. Yeah.
So our
Good
next
for this.
speaker is
You
Celeste
need
Hofsetter,
the-
and she's going to talk about rock stops or Rupture.
Okay. And I think you need the microphone as well. I have no idea how. There you go.
Okay.
Okay, great. It's all yours. There'll be a
Okay.
alarm at 10 minutes.
Okay, thank you. Oh, there it goes. Okay. Hi, I'm Celeste Hofsetter, and I wanted to first thank the organizers for the opportunity to speak today. And I'm researching the 2023 magnitude 7.7 Pazarcık earthquake and what may have stopped the rupture. And so again, I'll be looking at the Turkey earthquake sequence that happened in eastern Turkey. And so these are two dense offset maps, and they're showing the two earthquakes. We have the magnitude 7.7 Pazarcık and the magnitude 7.5 Elbiston. And we're able to see a good sense of the basically the offset. So the satellite is flying south, it's looking west, and we get this really good color, the sharp color here, that shows us the extent of the rupture. And so this is in the range direction, this is going to be in the azimuth direction. And so I'll be focusing here where the Pazarcık rupture terminates, and this is going to be the perturb segment of the East Anatolian Fault. And so it's an interesting area. We have the rupture we can see here with the yellow traces. And there was also an earlier earthquake on January 24th of 2020. This is the Elazığ earthquake, magnitude 6.8. And it happened right here in this section, which is a known creeping segment of the East Anatolian Fault. So it's to the southwest of Lake Hazar. And so we have a period of interseismic where we have creep but no earthquakes. And that's going to be for a period of about 6 years. And then we do have the Elazığ earthquake. So here's our interferogram. And so then we have a post-seismic period. And then we again have the Pazarcık rupture that comes up and terminates. And then we have another post-seismic period that we'll be investigating. Here we go. And the other thing that was really fascinating is that it was determined by Çikir et al. In 2023 that the Elazığ rupture was terminated or arrested by shallow fault creep. So we wanted to investigate if that could have happened with the Pazarcık rupture. Sorry, is it? Am I supposed to? There it goes. Okay, so we'll be measuring our fault creep that Romain just spoke about using INSAR data with satellite Sentinel-1, and then also a campaign and continuous GNSS data from our colleagues in Turkey. And so the three key questions that we're investigating is what is the creep behavior across this 3 time periods on the perturb segment of the East Anatolian Fault, and we'll be characterizing how it varies spatially and temporally, and then what impact it had on the Pazarcık rupture. So we'll be looking at this interseismic period for 6 years, and then our first post-seismic period for 3 years, and our second post-seismic period for about 9 months. And so here is our GNSS campaign data from our colleagues in Turkey. And so we have the yellow inverted stations, or inverted triangles that show their stations, and our area of interest is going to be here to the southwest. And they are showing in this profile here a creep rate of 5.9 millimeters per year. And they're also seeing creep up in this section that varies from 5.5 up to 6.8. And here's our first velocity map. And again, like Romain was saying, we're looking for that sharp color change across the fault. So we have the fault shown there in the black line. And so this area, we'd be interpreting as kind of like a faster creep rate. And then we have the paler color here, which is a slower. And down here, we're not seeing that sharp line, so we're interpreting that as no creep rate. This is a velocity map. It's made from over 2,000 area standard product interferograms, and we process the time series with MintPy software, and we make our atmospheric corrections with Error 5 data. And so we also have the inverted triangles that we compare our data to our colleagues in Turkey. And so we take their creep rates and we convert it to our line of sight rates. And we can see that it matches pretty well, which is giving us confidence in the data. And so here we're just going ahead and seeing our creep rates, or our impression of the creep. And we went ahead and generated creep profiles. And so our creep profiles are varying from about 0.4 centimeters per year to 0.6 centimeters per year up here to the northwest. And as we get to the center, it's about 0.05 to 0.15 centimeters per year. And down to the southwest, it's about 0. And we're using a velocity map for this time period because it is interseismic, so we're expecting the rate to be linear. And as we move into the other two post-seismic periods, we'll be converting to cumulative displacement maps so that we can get a sense for the afterslip pattern. And so here's our first post-seismic period. This is going to be cumulative displacement for the full 3 years. And we can see that we are getting, so this is a post-seismic. It's after the Alazig earthquake. So here we have the epicenter. And then we have our extent of the Alazig rupture. And we're getting our highest displacement at the ends of the rupture. And we're also seeing that our creep rate here, we're able to see is coming within approximately 10 kilometers of the Pazarcık rupture. And so the way we want to examine this is through differencing the time series. So we went ahead and took a profile. It's a 4-kilometer long profile across the fault. And we take the time series from the northernmost end, which gives us our red graph. And we subtract our profile time series from the southernmost end, which gives us our black graph. And when we subtract those two, we get the total displacement across the fault. So that's going to be our blue graph. And it is showing this time-dependent decay pattern with the afterslip. And so we went ahead and took a look at the southwest section where we had high displacement. And we can see there is a sharp increase in the displacement, and it takes place over a period of 6 to 18 days. And so, there we go. And when we take a closer look at it to isolate it in our INSAR data, it's an aftershock, so it looks like an earthquake. And we're not the first ones to find it. Here it is. And so this is again by Takir et al., 2023. And here is his aftershock. So we just found it in our data as well. And when we take our profiles across the fault, we can again see that we're getting high displacement here. And this is still high, but it does include the aftershock. And then it's very low, so we have 4 to 10 centimeters total displacement over 3 years up to the northeast. In the middle, it's about 8 to 12 centimeters, and then down to the southwest, it decreases from 0 to 8 centimeters. And as we move into our second post-seismic period, we can basically see that the pattern has reversed. So we're now getting our highest displacement down to the southwest, and we're not seeing much happening here up to the northeast. And so when we difference the time series, we can see that we're getting up to 6 centimeters of displacement over this 9-month period. And it decreases as we move northeast, and it basically reaches not discernible creep within about 15 kilometers of Lake Hazar. So we're kind of interpreting that as most of the elastic storage strain has been released by this point. And so a quick summary from 2014 to 2020. We had moderate creep rates of 0.4 to 0.6 up to the northeast centimeters per year. And then in the center blue box, we have 0.05 to 0.15 centimeters per year, and down to the southwest in the yellow box, we have approximately 0. And then it will increase, yes. Okay, and then it increases as we move into the post-seismic period of 4 to 10 centimeters total up to the northeast. The middle portion has 8 to 12 centimeters, and then down to the southwest, it's about 0 to 8 centimeters. And during the second post-seismic period, we have no discernible creep up here to the northeast. In the center area, it's about 4 centimeters, and then it increases to 6 centimeters down to the southwest. Come on. Okay, there we go. And so the way that we're kind of envisioning this happening is it has us thinking about like the 1906 and 1857 earthquakes that happened on the San Andreas Fault. And so we again had the earthquake initiated up on the northwest, and then it propagated down to the southeast and terminated right before that creeping segment on the San Andreas. And also in the 1857, it initiated somewhere up to the northwest and propagated down to the southeast again. And with the direction, it failed to really go into the creeping segment. And then also, if we look at the magnitude 6.0 2014 South Napa earthquake, we have the earthquake is nucleating in this area, and it propagates about 8 or 9 kilometers with very little coseismic slip until it passes this point, and then we get 40 centimeters of coseismic slip. And yet, this area that failed to slip a lot coseismically had a lot of afterslip. And so that is having us think about what we're observing with our data, where there's an area that had high coseismic slip with a Pazarcık rupture, and then we ended up getting a lot of afterslip in an area that had not slipped previously with the coseismic. So from 2014 to 2020, we had creep rates there of up to 0.6 centimeters per year. From 2020, the first post-seismic period, to 2023, we had 12 centimeters of afterslip that did include an aftershock of 8 centimeters slip. And then during the second post-seismic period, we had up to 6 centimeters over a period of 9 months. And we're kind of interpreting that the Pazarcık segment does have creep properties, even down to that southwest area that was not creeping previously, and that it could have plausibly stopped the Pazarcık rupture.
Yeah. Do we have any questions from students, postdocs again? You know, I really want to hear your thoughts. Okay. Anyone? Okay.
So the one slide before you showed that the high percentage of your the one slide before you showed that the high percentage is within the zone of the afterslip zone. So that means that earthquake started from the unlocked zone. So is that right?
Sorry, can you, the epicenter start, the hypocenter? Yeah. Which?
Maybe you can go back to the slide.
Yeah, I'm trying to. That's okay. Yeah.
Second last. No. Just the second last.
Oh, second to last slide. I'm sorry. Okay. So, are you talking about the South Napa?
This one.
Yes.
So the epicenter is on the eastern side of the afterslip, right?
Say that again?
The epicenter is the eastern side of the afterslip zone. So we expect the afterslip occur within the zone of the unlocked zone. But in your case, the epicenter is in the unlocked zone, right?
That's kind of how I was interpreting it. I was interpreting that it went through it. So there wasn't a previous creep here before the earthquake, but I was interpreting it as going through an area that really didn't want to slip coseismically, but once it reached that area, that was.
Suspect some nucleation started from the Pazarcık, right?
Potentially, yeah.
The
Yeah.
rupture has kind of as, you know, the coseismic rupture slants below the aseismically slipping code, so it initiated deep and then ruptured.
Oh, gotcha.
northwest,
Okay.
And then the creep filled in the upper probe.
Okay.
So it's still close to the part that's creeping, but it tunnels underneath.
Okay. Thank you. I didn't. Yeah.
Thank you.
So Sylvain, that answer your question?
No. So you suggest that between the Laser earthquake and the Carolyn Marsh earthquake, there's this creeping segment.
Mm-hmm.
But if you look at the local geology, all of the Laser earthquake area and this so-called creeping segment, it's all the same unit. It's microschests. There's no difference. So, and if you look at this example in the San Andreas fault, you know, that's where you have the transition from paleo-accretionary prism that's serpentinized and other types of rocks. So there is a match between different seismic behavior and different geology. It's not the case in the Pretoria segment that you talked about. So perhaps the story is a little bit more complicated than you suggest.
Okay.
So have you looked at the
Cool.
geology?
I have, and let's see if we can. So what I found on the geology was, because here we have this should be here, it's kind of pale for me to see, but the Euphrates River. And so more to the northeast, it's more volcanic, and down to the southwest is where we're getting the Pazarcık metamorphic rocks. And those, like, Josie Nevitt took samples from, and she talked at AGU in 2023. She did, like, rock samples on it and found some velocity weakening, velocity strengthening properties from those samples. But I don't know specifically, like, where she gathered them from.
Yeah, so if you find velocity weakening,
Yeah.
that doesn't bode well for food.
So it was velocity strengthening up to like 100. She was doing temperature and using that like as a proxy for depth. And so she was finding that up to like 100 centimeters, 100 degrees Celsius, it was velocity strengthening.
Yeah, that's less than
And
5
then
kilometers.
that's, yeah, and then down, and then at about 200 degrees Celsius, it became like velocity weakening.
So
Yeah.
that supports the seismogenic zone.
Yeah, and so she was, so she was thinking like that may have been why the Lazig earthquake originated, could have been a contributing factor to why it originated where it did. But could we talk about it more? Because I'd like to hear your thoughts. Yeah, okay.
I think Romain, you had a question.
Yes.
So in your INSAR data,
Mhm.
you see this aftershock to the west, and you see the creep to the east. Do you have any evidence for creep propagating or some kind of propagation signal between the Lazi earthquake toward the west? During that period?
We haven't been able to analyze it that closely yet. So I can't say if there's I'm not seeing anything in the pattern that's directly showing that yet, but I haven't looked that closely for it yet.
Just to comment on your geology thing, along the creeping section of the North Anatolian fault, there is volcanic basalts, there is metamorphic rocks, and there is limestone.
Okay.
All along that.
So all of the, yeah.
So sometimes it's just no correlation.
Yeah.
Sometimes it is.
Okay. Yeah. Thank you.
Okay, great. Thank you, Celeste.
Got it?
So our next speaker is Kumamoto.
Thank you.
Thank you. Thank you.
So he's going to talk about the near-field strong pulse caused by the coseismic depth.
Right. Can I stand there? Point out here. Okay. So hello everyone. So I'm Kurama Okubo and from the NIED in Japan International Research Institute. And today, I'd like to show our recent work about the dynamic rupture modeling. So our time scale is now in the seconds, and spatial scale is in the tens of kilometers. But we have one interest about the coseismic offshore damage and the strong short period pulse. Okay, first, let me first introduce the overview of our turret of the earthquakes. So this is a 2016, the magnitude 7.1 Kumamoto earthquake. This occurred in the south part of Japan, and that is the Kyushu Island. And this occurred in a very complex fault zone. Here they did some field observations after the earthquake, and then mapped some surface ruptures. But essentially, there are two fault segments. The first, the earthquake is nucleated from the south part of the fault. It propagates northwards, and then it goes to the end of this rupture. It's pretty much in the right lateral strike slip fault. And this is a very catastrophic. Actually, there are a lot of the houses that were collapsed. And moreover, the 36% of those houses, those damage occurred at this region and circled called the Mashiri town. And people look at what happened of the strong motion data at this location. And they found this kind of waveform. So this is the accelerograms. So north-south, and then the east-west, and then up-down the components. And you see that here that I annotated it, that 1 second is like that. So the spectrum is absolutely higher than 1 hertz. And when I computed the power spectrum density, and then it shows very rich in the higher frequency contents more than the 1 hertz. And this is very well discussed that the high frequency components is always enhanced in the subsurface, but this study, I focus the one more point that they all even observe very strong the short period pulse in the east-west components. This is also this has been discussed in the earthquake engineering side. What causes this pulse? And historically, I should review back to the 1980s. But the first is that those high frequency components can be amplified by the site amplification. So imagine that the subsurface is very soft. And then the ground shaking is amplified from the source. And they did the comprehensive institute studies, and then they found some amplification might occur in this region. And second, the option is about the second factor, potential factor is about the fault roughness. The roughness enhances the high frequency radiations, and this is done by the dynamic and the numerical models work. And they show that high frequency radiation is enhanced. I don't be against for those factors. What should be superimposed one more factor is our coseismic offshore damage potentially. So my question is does the coseismic offshore damage cause a strong short period pulse or not? So that is the focus today. Okay, so to do that, we did numerical models. And here, so my effort is I want to based on the observational results. So this is the comprehensive work done by the Yue and et al. 2017, they did the finite fault inversion, but using the aftershocks and strong motions and also the geodesy, the INSAR data, the GPS, whatever the data to constrain the fault models like this. And I take those fault models, and then actually my simulation is now limited in the 2D, the planar fault. So I make some cross section horizontally at depths of the 8 kilometers. And here, this is the fault plane they embodied. And the red line is I took the cross section to perform the 2D dynamic rupture simulations. Just note that the dip is not perfectly 90 degrees, but we have certain angle, pretty much the vertical. So we interpret it as a strike slip fault. And stress and friction parameters, we have the previous studies done by the Untitled 2017 that they did the planar fault without offshore damage, and then the boundary element method to understand the fundamental the rupture process of this work. So we took into account those parameters for stress and frictions. And finally, stress is in the order of these values and the friction parameters, and this is the fracture energies which we have to configure for the dynamic rupture models. And then our the modeling scheme, that is what we have developed for a long time about modeling both the failure of the main fault and also the off-fault fractures, which is we call the combined finite discrete element method. FDM, and the software is developed by the Los Alamos National Laboratory. So essentially what we are doing is that at each boundary of the elements, we compute the contact force, cohesion, and friction. And when the stress is perturbed by the dynamic ruptures, we have the perturbations on the interface of the elements. If it hits into the peak friction or the cohesion, it hits the cohesive peak, and then it breaks. We represent it for damage in such a way. So in this study, to investigate how the coseismic for damage enhances the radiations in the high frequency components, we did two cases. The one is a fault without no junctions in these rotations. And I tested the second one as we put some gap between the southern part and northern part. I have some data from some distributed deformations around this region. So it's published by Scott et al. 2016. So we refer those the geodetic observations to estimate, assume that if there is some gap between the segments, so that the coseismic for damage is enhanced. Okay, so here I want to show the result of the time ruptures. This is a movie. So before playing that, I want to explain what I showed. So here, the color contrast shows the particle velocity magnitude. So how much the velocity is going on around the fault. So you can see the clear rupture propagation afterwards. This is a scale. The length is in the order of the 10 kilometers. So let's play this one. Okay, so this is the cross-section of the fault geometries. The rupture propagates. And this is, the fault is connected. So rupture is fairly simple. Like propagates, supersaturation happens a little bit. So I don't get into details for this talk. And then the rupture hits the end of the fault. So this is what observed from the connected model. So for sure, this is very hard to identify the very enhanced high frequency radiation from this simulation. Just note that those are the tiny yellow lines is awful damage I discretized, and I will show in the later with the disconnected model where you can find more. Okay, so next one, yes. We have the disconnection in the segments. Pretty that, okay. So here, the tricky a little bit, the rupture fronts and stops in the segments, but slip accumulates. It breaks these segments gradually. And then the rupture jumps from the northwards, and then the break much more on these segments. And you see now we introduce a lot of the small characteristics in this system. So we expect that we have much more the high frequency radiations with this model. Okay, so the first look at how the the distribution of the high frequency radiation in space. So here, what I try to do is that we computed the spectrum of the velocity spectrum at each this grid where I put virtual seismometers, and then integrate the per spectrum density between the 4 and 8 hertz so that you can get the proxy of the kinetic motions with this frequency band. And the left is with a connected model. We have the certain high frequency, the local high frequency, the radiations at the edge of the fault. And I looked to the site that there's a very nice paper about the dynamic source effects of the Shiriwa and actually Alice, and they highlighted how the high frequency enhancement is occurred from is caused from the fault dynamics. But here, adding to our awful damage. In the right, we have the gap in the segments where we can find more intense high frequency radiations, and we expect that this can be this is a fact that we observed high frequency radiation in this rotation, and moreover the short wave pulse, which are how we can observe from our model. So this one is the actual waveform. So I plotted the horizontal, the motions, velocities of the north, south, and east, west, and this is the rotation at the red circle. With connected model, it is the one that we observed. And we have a strong pulse, and then I would like to refer also the Yoshi and Goto 2022. They also the model with this Kumamoto earthquake, and mentioned that the velocity pulse can be observed in near fault. And we are consistent essentially on that case. And then we see superimpulse of the damage, and then the waveform looks like this. So we add a lot of the small for the radiations and which has the more accumulation enhancement in the high frequency components. And when looking at the pulse, we just rotate it to search where we maximize the pulse because polarity and details is not fit yet. But qualitatively saying, we could observe the pulse in the disconnected model, which is comparable to the observations. So I think that this is a short message, my take-home message. But off-fall damage is one of the possibilities to cause this kind of shortwave pulse as well as high frequency radiation enhancement. Okay, so the almost conclusion, and the time is over. I think also thank you for your attention.
That there were these possibilities of fault roughness on site amplification.
Yeah.
Because have you tested this?
Also, thank you for it. So actually, I haven't tested it, but we are capable to test it actually. So afterwards, we want to include some heterogeneity in the medium, and then add the roughness with the fall damage, and then I want to distinguish if how much percentage comes from the heterogeneity of the medium, and how much pulse comes from the coseismic damage. That's my observation. Thank you.
Yeah, very nice study. Related to the previous question,
Yeah.
There were stations, borehole station, as you might know,
Yeah.
at the same site. So you have a surface station, borehole station.
Yeah.
And I remember if you take the difference, the wave
Exactly.
is quite different.
Exactly.
High
Yeah.
frequency,
Yes. Yes.
which suggests it's a side effect. So that was my interpretation. But you argue for the other interpretation, which was interesting, but maybe follow-up study on to look at the effect of side effect.
Yeah, so yes, first agree. So there's a side effect. My point is that side effect amplifies the high frequency radiation, but in the average sense, that's in the spectrum sense. So I think the short wave pulse is, I think, the key factor which really has to distinguish if it's coming from the site or the source. That's my point. Yeah, but yeah, so I should.
But I think Andreas also had a question. Okay, but you don't think?
Yes, so in your model where you have the two segments that are disconnected, you create a zone with heterogeneities that are of dynamic origin.
Exactly.
But the high frequency content of the wave field could come from pre-existing heterogeneity that could exist anywhere along the fault.
Mm-hmm.
So how do you, I mean, it could be that you have also strong motion created by heterogeneities that are not in your model, right? Because you assume that it's very smooth fault for the two segments. So how can you tell that it's of dynamic origin versus pre-existing? Do you see any signal in the INSAR that may help you in that regard?
Oh, okay. I think So what I can do is that I assume some pre-existing damage, for example, in the heterogeneities, and then run the simulation. So, but to do that, so I think that I need the very comparison between data and my model in the quantitatively, because the both the pre-existing the heterogeneity anyway contributes to some part of the high frequency components. While if I really want to say that this is coming from the newly created fractures, and then I have to do the quantitative comparisons between my model and data. So in such a case, I think the geodesy is very important because it's a quantified, so which I can compare eventually with the future 3D model, can compare with your model. I think to really identify how much the fraction of the complexity comes from my model. Actually.
So I was thinking, do you see evidence for more distributed strain in that area where you have the disconnection than you would see elsewhere along the fault?
Oh yeah, so let's see. I just quickly pop up the figure. So I refer that these are the studies actually. So just this is the overview. Is like they have the inside data, and then this is the connection that I put the gap. I put the disconnection there, and they have the discrepancy of the distributed by versus the localized the deformations up to let's say like the kilometer scale, which is a little bit wider than what I observed so far. So maybe my cohesion is too high, so that has a damage that is not diffused so much. So I have a chance still to fit my model to the data with those observations. Yep.
Same question.
There's a question there.
Sorry.
Yeah.
Your fault in a connected model is very smooth.
Yeah.
Do you think if you make it a bit more, so not necessarily using roughness at smaller scale, but if you have more like sharper corners locally, you could probably produce also some kind of more higher damage locally. And how did you decide to smooth in a way? Like there's a choice that I'm interested to hear your take on this.
Yeah. So my idea is so that's actually what I want to try to the next actually because the roughness and coseismic damage should have a trade-off a lot, and then I don't have an idea where we have a chance to distinguish between them. Yeah. Okay.
Great. Okay, thanks everyone for a great morning session. 25 minutes for coffee.
Hey. Thank you.
Let's talk a little bit. We actually have some ways to tell if that's a damage or side effects or things like that. I'll show you the paper. Wait, so it's in revision right now for SRL. So out soon. And
That's totally interesting to me. Because it has very fast, 4 clicks of water.
Okay. How about when you take my laptop here and we got a coffee and we can use like outside the like in the table? Like there's a table right outside of it.
Oh yes, exactly.
Yeah. Like I can show you.
Oh, thank you.
Yeah.
Absolutely. So I just use this connection to the C-plug or the HDMI.
But if you use HDMI, you cannot use.
No, I don't think so.
So my initial claim was saying
gradual increase. But if you look at the origin, like if you have like sensors on the photon there, don't you expect like still it's a transient nature after the discrete?
But do the transients add up to turn up, or are they little transients driven by something
Well,
that's
because there's no, this notion of continuous is somewhat, observational. Well, I would maybe you could clarify this point that the transient, what you just said is kind of intriguing. Because I also thought that it was composed of tiny things all the time.
Yeah.
It's just that we don't have observation to say.
To be fair, I still think it's.
Okay, let's go.
coffee. Now we will take coffee to judge.
Okay.
We judge coffee.
See you later.
senso di sciare è così, la R scende così. Parte. E se tu vai sul mio, trova se c'è il mio paper sulle microstrutture, ci sta, ecco. Se fai uno screenshottino con la cosa sopra, così non manco te sbagli. Guarda. Ma perché perché non è open access. Cristiano dice queste cazzate sono articolo pubblicitario. Perché facciamo una stagione geology e se tu per farlo open access devi pagare. E quindi non pago queste cazzate. E poi sono articolo pubblicitario. Non so 15 minuti, 10. No, perché comunque no? Niente, vabbè, dentini facciamo interventi. Dentini facciamo interventi. Poi c'è banda B, banda Y, almeno una banda B,
Sorry?
Yeah, I missed the time.
This stuff stays on the desk, no? The adapter?
This stays, yeah.
Okay.
The adapter, there's also a remote
mic.
control, yeah.
Dr. Andreas Rietbrock, and he's going to talk about imaging of the structure of the seismogenic interface.
Okay, so I would like to thank the organizers for actually inviting me and give an overview of how we actually can image nowadays this seismogenic interface. So what techniques do we have and how far can we push the resolution limits? And I also want to point out that actually this is a work we have done over the last 20 years, and here are some of the PhD students, postdocs involved. And since we do not have an active subduction zone in the UK and in Germany, this is mainly really distributed all over the world in actually subduction zones, which are normally not that well studied, like Japan or like Cascadia. So it's really trying to add to the multitude of subduction zones, and I still feel that sometimes we are really biased to 2 subduction zones where most of our analysis and new findings are coming from. So this is what we all know. This is just a little image of Thornley, how actually we interpret the subduction zone interface. And we have these slow tsunami earthquakes close to the trench. We have areas there which are seismic. We have areas which are seismic. Then we come into this big conditional stable region. Is it all A minus B or B minus A? And what are the signs? And sometimes it's rupturing, sometimes not. We are then getting into the repeater zone, and then we are coming into the area where it is sliding. And here is a cross-section that we all know. And what I just want to point out, in all these cross-sections, which are mainly coming from interpreting moment release, the interface is sometimes a thin line, sometimes a thick line, but that's it. There's no way that actually from the moment release we can find out what is the internal structure of this interface. So that is where my motivation comes from over the last 20 years, in and out. What can we do to really find out the physical properties to a resolution which might be useful in the end for the modeling community and for actually predicting large slip. So, what are the physical properties of this? Can we image this? What is the thickness? Do we have any handle on this? And at the end, can we also say something about the topography? And I found it very illuminating, the last discussion, so the discussion just before the break, and people were saying, oh, but it could be roughness, but it could be actually more kinks, but it could be really properties changing. So all of this, just from looking at peak amplitudes or phases in the seismic record, will be hard to constrain, because you have the trade-offs. It can come from any of these sources. We might be clever and find out that we can actually cancel out some of them, but it might be difficult in the end. So, what do we know? So, I went to the Alps once with Onno Anten, looking at some of these exhumed subduction zone seismogenic interfaces. And here is an overview of one of his papers, a summary paper. And what they are seeing is, and I believe what they are seeing, it was convincing to me in the field as a slightly trained geologist as well, that in exhumed subduction zones, we have scale lengths of 100 meters, of a couple of 100 meters, where they see the deformation zone. And inside these 100 meter scales, they have structures which are 10 meters above or 10 meters around, and that is where they think actually slip has happened. However, they really have a good spatial resolution, fault core zone of about 10 meters, but they don't know, was this really an earthquake? When did it happen? At what time of the seismic cycle did it happen? So timing is very, very difficult in here to have an understanding what is going on. And then we have seen a lot of seismic cross-sections with seismicity in the last 1.5 days. And here's one example for a seismogenic interface where we actually pushed about 15 years, nearly 20 years, how far can we get with the resolution? How thin can we make this interface? So, and even if I think about the talks this morning, about then thinking, oh, this is slip on the fault, this is deformation of the fault, it's very important that we know where actually the fault core is and what is on the fault and what is out of the fault. So what we could do then is maybe on a kilometer scale. So we were out 1 order of magnitudes. We were always writing proposals that we want to bring this together, but in the end of all this work, it was always a magnitude out. And of course, if you have 1 kilometer, 2 kilometers, 3 kilometers to play with, then all the models will fit. You will always and can use the seismicity to say, actually, my model fits, because there's no resolution that is in the error bar. What I also have as a little theme here, just to show you how actually seismology on the instrumental side is currently changing, is what kind of equipment, how much did we have to bring to the field. And for this study, which were the aftershocks of the Antofagasta earthquake, it was 2 20-foot containers for deploying 40 stations at that time, continuously recording, and we had 10 to 15 PhD students constantly changing batteries. That was state of the art with mobile networks. So it was a big logistical challenge. So, seismicity, kilometer scale. But then, of course, you might say, oh, we have so many other geophysical tools to actually image a subduction zone interface. So, seismicity I've already shown, that is what we can do. Then, of course, seismic tomography, local earthquake tomography. How far can we push this? And here you see one study, which was a local earthquake tomography study. It was actually carried out before the Antofagasta earthquake, so it was carried out in 2008. We had then 150 stations. Well, we could now fit 150 stations into 2 20-feet containers. So actually, it was getting better. We could do more for the same amount. And you see, we are here. That is the rupture area, actually, of the 1960 earthquake. And we are here at the Arauco Peninsula, where we deployed 150 stations to image in high resolution the subduction zone interface. And the results you can see here on the right-hand side. Still, look at the depth scale. This is 100 kilometers. So then seismicity is always looking very concentrated along a thin line. But what we could see is, yes, we can image quite nicely the downgoing plate. And what was actually much more interesting is that we could also image very high VPVS ratio directly in the downgoing oceanic crust. So that was for a 2D cross-section, and then if you do this in 3D, you can increase the resolution, and there you can see that actually the seismicity is really on top at the seismogenic interface. Still, the thickness here is much worse than the 1 kilometer I've shown before, and we have this very elevated VPVS ratio. And then, of course, you have to do something. So we played around, can we correlate this a little bit to GPS? So here we have now the locking, the inferred locking before the Maule earthquake. And we have our feature of high VPVS ratio spatially mapped. And now we can, of course, try to correlate locking with VPVS. And that is what we exactly did. So we have here VPVS ratio or Poisson ratio on this axis and the locking degree, and we see a relationship. Not very good, but we see a relationship. And if we then define 2 areas in here, based a little bit on petrology, and map then these areas back to the spatial location, then we can see that actually locking and low VPVS ratio nicely fits together. And opposite, if you have very high VPVS ratio, actually the two plates are more or less gliding along. However, what I said is we were cheating a little bit, because that was the average VPVS ratio of the whole oceanic downgrowing crust. It didn't tell us directly anything about the interface. So you could have actually here numbers of 5 at the interface for the VPVS ratio and 1.6 in the oceanic crust, and we would get more or less the same results in our tomography. So tomography, even right now, may be resolving on 2, 3, 5, 6 kilometers, not better. So what you could do then is, let's look at receiver function images. Very popular, very cheap to do, very easy to do, and that is quite a recent study here from Kim et al. In 2021 for the Japanese subduction zone in the north. And the problem is when you're doing receiver functions offshore, where it is very, very interesting, everybody knows that you have a very thin sedimentary layer or a thicker sedimentary layer, and that is very water saturated. You get reverberations in your signal from these sedimentary layers. And that is actually what is shown here. So you then get superposition of the signal coming from the sedimentary layer here and the reflections or conversions from the moho, which makes it nearly impossible to really define the structures in the downgoing slab. And that is why, although you have loads of observations, temporary OBS station, cable SNet, lens stations, that actually you might see the top, you might see some internal reflections, and here they even did a lot of corrections going from the raw image, correcting for the sediments to come here to this image, but still, resolution is in the order of few kilometers, 5 kilometers, no real internal structure. So let's now use the highest resolution that we can, and that would be multi-channel seismics. 35,000 US dollars per day, but at least this is the best you can do, and this is what oil industry is doing, to figure out what is the structure. And that is now here an image for an experiment offshore Alaska, which was done 10 years ago, but now the first results are actually coming out. And what they are seeing here is that they see something like a reflection from the top of the downgoing plate. That's these red dots, that's the upper part. And then they see a widening of a channel here, or an interface zone, which is about 1.5 kilometers here, and then at 28 it widens up to 2 kilometers, and at 45 maybe 50. If you look in more detail into this, I find it quite interesting. Why did they go down here? There are also reflections up here, so it is not that conclusive in some way. It is very good. It is the best we can do for structural images, but nobody tells us, is this the interface? And I think the interface we can still believe, but what is this? Is this internal structure just in the downgoing slab? Or has this something to do with actually processing at the subduction zone interface and stray? Or is it inherited structure which is being subducted into this? So all the techniques we have some upsides and some downsides. And I just want to separate them between what is our spatial resolution and how much can we actually resolve the temporal variations, and how much can we relate this to some aftershock activity, for example. So I started seismicity 1 kilometer, still 1 order of magnitude out what we would need. Temporal, it's very good. We really see the evolution. We can look at pre-shock, aftershock sequences. We can look at all this build-up, and we have a very good temporal resolution. Tomography, although you hope it's a little bit better with spatial, so the hypercenters are getting better located, but still that's 1 kilometer. Temporal resolution is fine. I can't see right now really good applications of receiver functions. So I hope no receiver function guy is in this audience. Otherwise, they might not like my statement. But you have the problem with the sediments, and you have then the problem with tilt. You have a lot of problems that you still have to solve. I don't think it's impossible, but there's still some more work that has to be done. And then multi-channel seismics, very good in spatial resolution, thin reflection bands. That would go in the order of 100 meters, but we don't know what these elements mean. So we have to do something. We really have to do something. We really have to figure out what can be done. And then I think for onshore, for crustal faults, this is really one of these seminal papers of Waldhauser and Schaaf, where they used then double difference relocations with PICs, but also with cross correlation to really enhance the seismic image, to really go from what you get from a catalog to really defined faults. And that is not in this case that they added stations like in the morning, so that they have then a higher resolution. That's actually just increasing our resolution by using more advanced techniques. So that's cool, but in order to do this, you need loads of events. You really need a complete catalog, and that is why it was very difficult for all these temporary deployments to actually go in this direction, because some poor PhD students actually had to pick these phases. And you have 3 years, so you can do about, let's say, 500 earthquakes, and then you are happy that you have a local tomography model, you publish it, and you get your PhD. The data might contain many, many more earthquakes that nobody looked at, and we didn't have the tools. We could not, actually. Or I should have hired 20 PhD students every year to actually go through all the data, but that was also not really a possibility. So, Felix and I, a long time ago, did some relative relocations for the subduction zone in northern Chile, and we came up there with a double seismic zone, separated again by 10 kilometers, which was not known before. In both of these layers, we had down dip extension, so a lot of normal faults, and we attributed this, of course, to hydrated oceanic mantle fluids coming up, standard interpretation. I just put this up because in 20 years ago, we also checked what is the difference using a 1D velocity model and a 3D velocity model. And we concluded at that time, we find, however, the differences between solutions based on the 3D and the layered 1D model are small. And at that time, we thought, we are great, we can do 1 kilometer, less than 1 kilometer. And we wrote this, and I completely forgot. It was off my mind. I didn't think about it anymore. And then this problem was still there. 100 meter scale, can we do something? 1 kilometer scale, we can do with seismicity. So what happened then is, in the last 5 years, actually observational seismology completely changed on that side. Here I just want to show how it is changing with a little experiment we just did before COVID lockdown. There was a Dürres earthquake in November 2019. We went there with 30 stations to record the aftershocks in that region. And as you can see, these are locations in the middle of Europe, lots and lots of stations, very close. So we are here in the Balkan, Albania. So I was still very much astonished that actually our location accuracy in this teleseismic regional sense for the different agencies, they agreed on the mechanism, but where actually the main shock was located was on that scale for magnitude 6.4 everywhere. Because the rupture will be something like that. So that is where we are. And if we just take catalog data from the global agencies, we are still in that world that actually you can shift by not tens of kilometers, by kilometers, this scale. So we deployed there the stations, and these are now really cheap stations. These are the yellow little bit here, there is 4.5 Hertz geophone. Nothing fancy, not a broadband sensor. Costs about $200, $300. This is also not a broadband sensor, but very heavy. That was the old generation. So that is the network, and we recorded 10 tons of aftershocks. So the lucky thing is machine learning was just on its upturn. And we were lucky that we actually had funding, the GFZ and KIT, for two very, very good PhD students, Janis Münchmeyer and Jack Woolham, who developed SeisBench. And I will talk to you on Thursday, if you're interested, what SeisBench is, how it can be used, and how easy it is nowadays to actually analyze tons of data. So, what did we do? We applied FaceNet, Sue and Barossa, through the SeisBench interface. And what you can see here is it picks the P wave, it picks the S wave, and it does it when there's a good signal to noise ratio, and also, especially here for the S, when it's not so good signal to noise ratio. For the P wave, actually, AI or machine learning procedures are not getting so much more information out. So a good STI-LTA trigger can do more or less the same thing as AI. AI is doing it a little bit more consistent. The dramatic change that we see is for the S wave. So the S wave, we now get nearly the same amount of high quality S picks than P picks. And the other thing is, an STI-LTA never told you that's a P or that's an S. That was an inference. So the two things which really changed how we do seismology is that we get labels, we know it is a P and an S, and that we get a lot more S phases, and therefore we have P and S, and therefore we can constrain the hypocenter location much better. So you pick this, you associate them, and then there's always this backslash, are these real events or do you just correlate noise? So is this really something we should believe in? Or is this distributed or localized seismicity actually only highly correlated noise, and the machine learning picks are giving us not real insights? So this is the local magnitude here, that is time. That was the Dürres earthquake, so it's the aftershock sequence. That is what the Albanian network detected before we came in, with a magnitude threshold of about 2. And this is now the seismicity we could detect and the aftershock sequence of this. And now we zoom into this period in January, from the whole of January, and what you can see is actually here, it's still magnitude, But now you see that actually we have this diurnal pattern fluctuation that we can pick events, and sometimes we can't pick the small events. And if this would be correlated to the daytime, I would be very worried, because it could be really cars coming by, and we would then see actually what the anthropogenic noise is doing, and we would just address it to events. However, if you now plot the detected and associated events as hour of the day, we see that all these small magnitude events are coming in during the night when it is quiet. And here, these curves on top are actually the noise curves of the seismometers, the background noise, and there's a nice anti-correlation. So from that side, we can be very sure that we actually detect something. If we do this, and if we have a very large network that is now being feasible, you can see now amazing things. So this is a record section of an event in the Alps. These are 1,000 broadband stations deployed during Alp array. It's reduced time here with 6 kilometers per second. And you beautifully see, okay, we can pick the PG, we can pick the SG. We do an amazing job in picking the PN out to 700 kilometers. And that's still single channel. So I think if we now think about machine learning where we actually take the wave field in, we can even improve on this. What is even more amazing is you get consistent SN picks, which were unknown for the Alps. Because on a single trace, it's really hard for a PhD student or a senior scientist to say, that's the arrival of the SN. But these machine learning tools actually can do it. We get overcritical PGs, which we are not using in travel time tomography right now. But same with overcritical SGs. So there's a platitude of more information now available, which can help us in the future to constrain much better our models. So that is the background. That is where we were. We now have the tools. So we're lucky, no, we planned for it, no, we were lucky, to actually record something in a subduction zone setting. And that was actually in 2022. When we did this Duris earthquake, I was actually on a French research vessel trying to do an offshore active seismic refraction experiment when the pandemic did strike. In the end, we could do 1 week of our experiment. We didn't have COVID. We were all sitting on this research vessel. The whole world was going mad. We were nice and secure. But then the French government decided all ships have to return to France. So we were sitting in Ecuador. Ecuador was closed. One of my PhD students was actually on the last flight going out of Ecuador. If he would not have made it, he would sit for the first 3 months in Ecuador without any chance to go back to Europe. So we were sitting there. The scientists were, oh, let's carry on. We have food, we have diesel, we have our experiments, let us keep busy. The seamen wanted to go home. So at the end, I spent my cruise actually not doing science. I traveled from Ecuador to Brest by boat, which was a nice experience, not so nice. And we were watching from the outside what is happening to the world. So that happened in 20, and luckily the French research organizations were so nice that we could redo this cruise. They were really accommodating, and I just have to thank them a lot that they made it possible that we redo it. So then we went back in 2022. We recorded actually a 5.8 earthquake at the seismogenic interface. And what is the region like? So you have the Pedernales earthquake here in 2016, magnitude 7.8, and that's the rupture area. And in the background, you have the locking. So it's really at the transition between high locking and low locking. And there's this debate of the 1906 magnitude 8.8. How far is this reaching to the south? So we could record this earthquake, and we could record this earthquake with a very high dense network of 4.5 Hertz geophones, which now fits into 4 suitcases. So we are going from 2 20 feet containers to 4 suitcases, and even doubled the number of stations. So that is where we are with these nodal stations nowadays. So we deployed March 15th to May 26th, and then we use all our new techniques that we developed during Corona to actually analyze this sequence. So we used FaceNet to do the picking, we used HEX, which is an associator for the event detection, and then we went more or less the routine down as we set them up, the workflow. We had the 3D, the 1D and 3D velocity model, and the big thing is we also used heavily cross-correlation. So we are not just using the original picks. So Caroline actually also used all cross-correlations, and we even went into traces where there was no pick to do the cross-correlations to really get a very complete data set. In the end, we have about 1,500 located events constrained by 2.5 million relative arrival times. And with a median location accuracy of 50 meters. So we are now really in that world that geology are seeing in exhumed subduction zones. And due to the dense spacing, the magnitude of completeness is about 1. So how does now a subduction zone interface look like when you're doing this? And these are now the absolute and relative locations. So here is the main shock, somewhere in here. There are GPS stations, but it is 5.8 at about 22 kilometer depth. So you can see a little bit of a signal, but maybe only on one station, and it's not that convincing that you really have a good signal. We can relocate all the seismicity, these 1,500 events. Thrust event, that's the main shock. There was a foreshock, magnitude 2. We didn't look so far really in detail into any of the foreshock sequences. And all the aftershocks are having more or less thrust mechanisms, except this cluster here, which has normal faulting, but this is really off the subduction zone interface in the overlying crust. You can see now, and here it's now 15 to 25 kilometers, how nicely the seismicity is focusing on the subduction zone interface. That's a model of the interface by Font et al. And the dip is a little bit different to what we are getting, but actually the depth is quite good. If you would plot here SLAB 2.0, it would be here. It would be completely out. And that is unfortunately what we can see in many of our local studies worldwide. SLAB 2.0, it's nice, but it's not very accurate in depth in many positions. So we see the sequence. Here is all these thrust events. And we can now see what can we actually get out. What physics can we get out? Here are just the numbers for the cross correlation. And in the end, we did this in a 3D velocity model. So that's what I said in the beginning. we knew we have to use a 3D velocity model to actually go beyond 1 kilometer in resolution. So 2 seconds around P, 3.5 seconds around S. Frequency range is 2 to 10 hertz. Threshold of the correlation is 0.75. And that is the most important thing, 2.5 million relative times. This is to show you again, we stated this 20 years ago, what is the difference if I use HypoDD, which is a 1D velocity model, and TomoDD, where we use the 3D velocity model. And you can see that actually it is much more focused. This is already good, but if you do it in 3D, you really can get to sub-kilometer scale resolution. So unfortunately, you need a 3D velocity model. So you have to do your tomography anyway to actually put this up. But in this case, we already had it with a PhD student at KIT. And nicely, Caroline found out exactly the same thing that we found out 20 years ago. The difference is 1 kilometer, and you have to use it. But I forgot, sorry. So, what you then can do, you can now project all the seismicity, all the aftershock seismicity, since it is so nicely located, just on a west-east profile. And then you can calculate the envelope to the seismicity. So you can now start really defining thicknesses based on data. So we don't have to say, oh yeah, this earthquake might belong to it, this not. We can actually now calculate an envelope, give some criteria, and say, what is the thickness? If you now rotate this, so make it flat, you can then read out here what is the thickness of this seismogenic interface. And since the location accuracy is about 50 meters, 50 to 100 meters, you can then also start thinking about what's the topography, what is the changes of this interface at depth. So the median thickness we are getting is about 250 meters, and the average height of topographic features is in the order of 200 meters. That's the range which comes out of this data set. And that nicely correlates actually with these conceptual models of Kirsty based on assumed subduction zones, where we actually have this fold strand thickness, this total fold thickness, which is in the area of a few hundred meters. So that is nicely fitting to geological observations. Now we can look even in greater details into some of these clusters, because it's amazing if you have so many earthquakes, how many repeaters or very well cross-correlated events you can find. So when Caroline showed this to me, I thought, oh, she just scaled the same event up and down. So she just made this up. So, because if you look at this frequency range, in this frequency range, it's very hard to actually find a wiggle which is not similar. So if you have this very high similarity, then you can push your location accuracy even further. So now we are looking into the frequency range 4 to 12 hertz, which is really accommodated then also to our very cheap 4.5 hertz geophones. We now use the whole window length, 2 times TS minus TP. So really looked for repeaters. Medium distance scanned is 10 kilometers. Cross correlations are discarded when the signal to noise ratio is less than 15. So we really only went for the high quality events. And we said that all of them all observations had to be better than 0.75 now in this whole length, which is very hard to accommodate. to actually put them into one family, into one repeater family. If they have negative correlations, we completely discard them. And that is actually something I think we should look into this in the future. Why do you get minus 0.8 correlation? Where you know that you didn't flip your geophone, the polarity, okay? Nobody went there, so then it would be easy. So we did this, we relocated them, and then we were interested in the spatial distribution of these streets, of these clusters. So we used a very old method I developed or I took up during my PhD, which is a 3-point method which I used in the Gulf of Corinth to find this low angle normal fault detachment. And you just have 3 points. With 3 points you have a plane. With the plane you have the normal vector, so you can define how it is orientated. And you just use all combinations in your cluster, and in that sense you can do a statistics which is more or less robust. And we use this. So what did we find is that actually all these families also coincide in their dipping with a down-going slab. So it's nothing like perpendicular, they are all parallel to the subduction zone interface. So it's not cutting into the slab, it's slab parallel structures. That's the main take-home message of this part. So now we have this, then we can look at the thickness. And if we now only do this analysis for the thickness, we come up with about, what did we write down? Is it 20 meters? No, yeah, somewhere around there, 15 to 20 meters of the thickness of these streaks. So how we interpret this is that this is actually now one of the features you see in geology, what they attribute to one fault zone, to one event which has happened during the seismogenic cycle. So if they are highly correlated, it means they happened on the same plane, and the thickness of these events correlate to what geologists would say this is one fault strand in the deformation zone. So I haven't shown you, and that's coming now, how does the interface look like? We have seen the overall feature, thickness of about 200 meters, topography also in that range. And now we just zoom into certain areas. So here's, for example, this area B, where you can see maybe you have 2 fault planes. All these figures are really in kilometers, so this is only 19.5 to 17.5, so this is 2 kilometers. So one line here, one line here. If you go to this area C, you see there's a big proportion which is just one interface, and in blue is actually these highly correlated families. So there we know definitely it's a very thin strand. And then at one point at depth, it just gets wider. It's the same thing here. You have 2 different strands. In blue again, we have these calibration events. And then, of course, some of them, families, do cut in the other direction. But overall, the feature is parallel to the subduction zone interface. So we now know that actually when we look at this seismicity, that's all happening on the interface. That is the process of aftershocks happening at the interface, and not somewhere around in the deformation zone outside mapped into it. So what we can now look at is actually the time evolution of these aftershocks. What are they doing over time? And since we know they are happening in the interface, we can actually now estimate the area. And since we deployed by purpose all the stations before the main shock, we have the whole sequence. So what you see here are now contours of the aftershock front. And it starts here with 0.1 hour, so 6 minutes. And it goes then out to 1 hour and then here to 100 hours. So it's really expanding over time. If you now plot this as time after the main shock in hours on a log scale and the aftershock area that we can now determine with our aftershock sequence, you see that actually this is the observed data. If you just plot more or less a straight line into it, this is more or less proportional to log t. Yeah? If you have an afterslip model, this is slightly deformed, and it more or less fits. If you put any diffusion in there, that is what then this black curve is, you have a big problem to fit what we are seeing. It's not really explaining what is happening. The problem I said I think we had so far is because this is 10 hours after the main shock. If you have standard STA, LTA triggers, they are constantly saturated. The seismicity will not be detected because you have so many aftershocks that actually they never reset to detect a new one. With machine learning, it's a little bit better. I don't think it's perfect. So what would happen if we would say we have missed events? Then actually this would go up even. It would not go down because this is the front. It might go larger. So it's even going further, or the worst case scenario would be it would go further away from the diffusion. But you can only separate it if you have these first 2 decades, so the minute scale and the hour scale, then I think you can separate. So then what we have are these main aftershocks, are here indicated in red, and you can see that actually here there's a little jump, but here something more fundamental is happening. So it's slowing down in some way, the growth, and you can see this here, it's slowing down, reaching this top, and then it has to wait. There are not so many aftershocks produced at that time than actually we would anticipate. What we also see then, before, at this tip, before this larger aftershock, we see this alignment of seismicity. So the aftershocks are propagating out, and they are hitting somehow something that they can't propagate even further to the north. So if we look at this in a cross-section now, so we are looking at this cross-section through this alignment of seismicity, we are coming from here with the aftershock front, going up, and that is where the aftershock seismicity was halted, where we actually go from a single plane, very concentrated, to a more diffused multiple plane aftershock sequence. And that is exactly when the largest aftershock happened. So it's really structural controlled, or we propose that it is structurally controlled, that actually the aftershock front propagates, there's some physical changes in the properties, and then it breaks through. So this can also be then imaged as the thickness, and that is where it was halted. The thickness of the interface has changed, and therefore the aftershocks have complications to actually jump onto this different scale. So, what were the conclusions of this study? The relocated microearthquakes yield an exceptionally clear picture of the plate interface. So 100 stations, 2 suitcases, 3 suitcases, magnitude 5.8, happening nearly every day or every second day. We could actually roll this out now. We could really go to many places and actually double check what is it. Costs of these instruments might be $100,000, not more. cost of deployment, maybe $10,000. So it's not a big thing anymore. And we have actually a lot of candidates now because we can do it for smaller earthquakes. We find several mostly subparallel fault surfaces. That's the main take-home message. We can constrain the thickness, and the deformation is subparallel to the seismogenic interface. The seismic deformation at the plate interface is not concentrated on a single fault plane, but instead is distributed over several distinct fault surfaces within the subduction channel. And diffusion processes really doesn't seem to explain the seismicity, the time development of seismicity. Where is it going to? So you can all look at Caroline's poster outside. This is just now going back to Maule, where she now did the same work in 3 weeks that I did in 6 months at Caltech, but getting 5 times more aftershocks. So that is what has changed. We see now in this lower plane of seismicity, which correlates very nicely to the high frequency radiation, to the back propagation. She sees a lot of these streaks in seismicity at the plate interface of repeating events. Side view again, this very thin layer, and again we see these steps like subparallel faults. If you go to northern Chile, and that is work by Jannis Münchmeyer, then you can see more or less similar things. So this is now the whole IPOC catalog relocated for 3 years, and you see beautiful the seismicity.
It's not IPOC.
It's IPOC plus, or what is it?
I mean, it's the deployment that was done by Frédéric Tillman and myself.
Okay.
So it's not IPOC, it's temporary deployment.
It's temporary deployment. Okay, sorry. So, what are the take-home messages? We can now image seismicity in the 10 to 100 meter scale along the seismogenic interface. It's possible now. So what I said in the beginning, we can't do it. I think due to machine learning and the things we all learned, we can now do it. Development in new seismic instrument is dramatically changing. So what I pointed out, we went from 2 20-foot containers to a bunch of suitcases. So, and that will even change. In all these watches, in all your phones, in everything, there are seismometers. And the development of these little chips are not driven by seismology, they are actually driven by tech companies which want to use it as wearable devices. So we have to just hop onto this, try to use it. And then we will not have hundreds, we will have thousands, 10,000, 100,000 sensors, which then will open up observations of the seismic wave field that we do not have so far. We are still very often single trace, single station analysis, and then putting things together. We have to go to the next level and actually push this. This will even getting more dramatic with DAS, where you have a much denser sampling, only one direction, but the combination of these long deployment capable nodes and DAS, we have hundreds, thousands of channels. Machine learning techniques are game changer for seismic picking and event detection. It really changed how we do seismology on that front. And as I said, the analysis we now do, we would need in 5 years ago, 20 PhD students. And then it would not be as good because it would not be that consistent as these techniques are. And where we are now struggling is we are so good in extracting all these picks and events that actually all our computer codes are breaking down because they were written 30 years ago in very old Fortran, and you cannot just make the core memory large enough so that it works. We have to really revisit all these codes to really try to get most of the data. So what we are doing right now are really shortcuts. It might be possible, and I have now a master's student working on this. Can we estimate what I set out now, the physical properties in between these events? Can we estimate the VPVS ratio in this thin layer of seismicity? It should be possible, but we have to do a little bit of coding to get us up to speed to modern technology. Thank you.
So similar to what you're doing here. So now questions, great.
One question you almost replied in your last sentence, that is, what do you think is the way to get on this high resolution subparallel photo the VPVS ratio?
Say again, because it was so noisy here.
What is the way to get higher, given the higher resolution that you have of subparallel photo, what is the way to move to get the VPVS ratio on this so tiny scale?
Okay, so it is really the way to go from location to tomography. So it's really the simultaneous inversion for both. That is what will get us there. That has some challenges, and you need a lot of data, because I think we are now in this range where we actually only can get the accuracy of our picks up to even better uncertainties when we stack a lot.
And the second is a comment, actually. For the correlation, it goes -0.08. I just read an article from a GFZ guy, Seismo-Geodetic, and it's called repeater and anti-repeaters. So it just shows a lot of possible projects for adding a source that is reversed.
Yeah, but still for the physical process, I find it a little bit difficult.
Yeah, this directly a follow-up to that. I was also wondering if you look more carefully at these possible end effects.
No, we
because
haven't.
in this environment, you could have wedge faulting, right?
Mm-hmm.
That's one of the mechanisms of
okay.
the large
Yeah.
deformation
Yeah.
that geologists see.
Yeah.
So you could maybe have evidence of
Yeah.
that. That could be interesting.
Yeah. We just discarded it right now because there were so many other things to do. Let's make it easier.
Get it out of the trash can.
Exactly.
So, Sylvain and Lingsen, Romain.
Okay. So, can you tell the difference between subducted channel and simply the oceanic crust thickness with various layers?
So the oceanic crust there in all these is about 6 to 7 kilometers of thickness. So it's much thicker than what we are looking at. The geology there is that you have a lot of accreted terrains there. So actually in Ecuador, the overriding plate and the subducting plate from their physical properties are not that different from the material because it's more or less both oceanic crust which interacts. So what I think much more is that this is the interface. What I always find puzzling, but maybe some of you could actually tell me, so if we have strike slip faults, then these ideas of Faulkner and all of this of the damage zone, which scales with the length of slip, works quite nicely. If I go to a subduction zone, so the overall slip is hundreds kilometers, but still the interface that we are imaging now is very thin. So if the scaling relationship we have for crustal faults would be the same, we should see a damage zone which is 2, 3, 4, or 5 kilometers wide. Maybe it's always new material that helps to actually constrain it, but I have no idea.
Well, just a comment on that, in our simulations, the damage actually saturates in the end. So there is, it doesn't have to be like the larger the cumulative sweep, the wider the fault zone. So.
Okay.
But Lingsen and Romain.
Great talk, Andreas. So for that 0.75 repeater criteria, so I get that repeaters need to be close for them to have high correlation. What's the evidence that they also have to be on the same fault plane?
So, good question. So what does it mean on the same fault plane? So I think we really, if we ask these questions, I would like that we ask them in the future also with the scale lengths what we mean on the same fault. So if we mean on the same fault, which is 200 meters thick, then I would say definitely yes. If we say they have to be on the same fault in the orders of 10 meters, I don't know. I really don't know.
Is there a reason to pick 0.75?
We could do it with 0.8, we could do it with 0.7. It would not change dramatically the results. It's not a critical parameter because we have loads of events. If you only have a few events, then of course these selections become very important because if you go too high with your cross-correlation coefficient, you will just have one event. If you go too low, you have a lot of garbage in there. So the only way forward to solve this is having more events. It's really observing more seismicity, detecting more seismicity.
Romain?
Thanks a lot. Now that you know exactly where they are, or almost exactly, how big are they? How big are they compared to their geometry and the size of the megathrust? And can you relate that to single asperities that we see in the field? If we're talking about a magnitude 2, how big is it? And that kind of thing. And the second corollary question is, are these from between different planes, are they different? Do they have different onset in the first arrival, slower, smoother, faster? And can we relate that to differences in whether you're in the basaltic part or in the sedimentary layer or in the subduction channel or...
Okay. I think all nice questions. This is a paper of 24, so we have a lot to do. There's a lot which can be done. So Caroline and I thought a lot about what can we now do with this data set. And of course, it's now looking into source parameters, estimating sizes, all of this. In the paper also, we started to do a little bit conclusion, can we estimate now the strain rate with a lot of assumptions. And I didn't want to show it here because there are a lot of assumptions in there. So I just stick here, what are our observations? So now I think we should go further, taking from the observation and now exploring in these different regions. If we now say, oh, can we distinguish what happens in the sediments, what happens in the basaltic material, who is telling me that there are still sediments? Who is telling me that there is only basalts at 20 kilometers depth?
Where's Oki?
Nobody can tell us.
Yes, so very nice talk, Andreas. So you're using the seismicity to make inferences about the structure. And when you do that, you're assuming that the seismicity is representing the structure in the long term, right? So I wonder to what degree the snapshot that you have, which is very limited in time, might be actually not representing very well your overall structure.
Yeah.
So my question is, have you looked at how the pattern is evolving? For example, if you do the clustering of the seismicity, not using the main shock, but the secondary aftershock that you have in your time series?
No, we haven't looked into this because we were right now interested in what structures get activated. So that's what I want to say. It is what structures are under relatively high strain rates active. And that's what we can see here in an aftershock sequence.
So do they show as secondary aftershock sequences, or are these independent events?
There are secondary aftershocks in there. You can see little bumps in the number of events, so you could decluster them. So what we haven't seen, we didn't look here, but what we did for the Duras earthquake is really you can see streaks, how actually aftershocks get reactivated or activated, and how they follow on some of these features. And some of them are active in the beginning. Some of them are then only coming live 2 months after the main shock, but they are then related to a magnitude 4.5. And you see then nicely that the aftershocks also lie on a plane and give you a very precise image.
One last question, yeah.
I'm curious about the aftershock So you mentioned that the largest aftershock has some delays. Yeah. So is there some structural change between the very narrow zone to the more wider region? But, is there any slight change of the topography of the?
So the change is in the thickness of the seismogenic zone. So it's not directly the topography that we want to, that we can see. Yeah. It is actually
so where is the largest aftershock?
Here, at the intersection between single plane to multiple plane aftershocks.
Okay. Not topography.
Topography. So topography and thickness, okay. I think this is more robust, the thickness, than the topography. That's why we use the thickness.
Okay, great. Thanks, Andreas. So our next speaker is Soquet, and she's talking about initiation and propagation of a shallow slope event.
Comment ça marche ce truc? Dans mon cou. No. Okay, can you hear me? Yes. Yeah, thanks. All right, so today I'm gonna talk about South America again and Chile. So this is a work that we have done in Easter together with Janez Münchmeyer and Diego Molina. Diego is here, so you can maybe find him in the room, together with our Chilean colleagues. And the objective of this talk is to look at one slow slip event that we have identified in Chile and try to see what are the interactions between this slow slip event and seismic rupture. So do all slow slip events lead to fast earthquakes? Of course not. But still, we can probably monitor the link between slow and fast earthquakes. And in this work, I will show that we can also capture the initiation of the slow slip event. So for that, we use geodesy and seismology and machine learning. So it was good to have Andreas talk before, because it was a great introduction. And also, he showed the results, so it was perfect. All right, so the area that we're interested in is here in Chile. So it's an area where we have the Copiapó Ridge that is subducting. It's an area that is known to act as a barrier to the propagation of large megatrust earthquakes. So you see here the historical seismicity. This is the Copiapó Ridge that acts as a barrier to the propagation of earthquakes. Here you have the interseismic coupling. You see that this area is poorly coupled. Another thing that is really interesting in this area is that it's the area where we find slow slip events in Chile. So far, mostly deep slow slip events have been found in Chile. And here I will talk about a shallow slow slip event that we discovered in 2023. So it's an area where we have also regular seismic swarms. So we have done intense monitoring in the area by deploying seismological networks and also GPS networks in the area. So as I said, in this area, we have the subduction of this Copiapó Ridge, which is a chain of seamounts. And so when you look at the gravity signal associated with this chain of seamounts, you see positive gravity anomalies that is associated with the seamounts. And here you can also image some local positive gravity anomalies that are probably associated with subducted seamount here, and also at further depths here. So this is we interpret this as a series of seamounts that are subducting below the megathrust. Then we studied this slow slip event in 2023. So we have done this deployment using GPS and seismometers, but we are also using all the GPS data that are available in South America. So if you want to use a GPS time series, you can go to this site and you can click on each GPS stations. You will see the time series. And you can download most of the data. And here is the event that we are interested in. So here you see the GPS time series in north and east as a function of time. Here you have earthquakes, and here you have this slow transient and small transient event that you can see. So let's zoom on that. So here are the detrended GPS time series at several stations. As you can see, the transient signal is pretty consistent from one station to the other. And please look at the scale. It's a pretty tiny signal that we're looking at. It's about 5 millimeters on the east component. So we can see that the stations start to move in this area, and then the movement increases and expands on both sides. And in the end, we have this distribution of the slow slip event. So the slow slip event, the duration was 5 weeks. The geodetic magnitude was 6.6, and it had bilateral expansion. So this is what is seen by the GPS. And as we have done also a seismogeodetic, seismological deployment together with the German and Chilean colleagues over this area. So because it was temporary deployment, we had, going and so installed stations and stations that were uninstalled. In total, we had about 100 stations that were running simultaneously. And so at the time of the slow slip event in 2023, it's about that there, where we have in the area of the slow slip event, mostly our deployment. So Yannis did this waveform picking, etc., using size bench, then associated the phase, absolute location, got a catalog. Obviously, it was more complicated than this because he did model velocity model estimation, cross correlation, relocation using Groclust, estimated the magnitude, and eventually got the catalog. So it's about 150,000 events. The absolute location error is below 3 kilometers. But the relative relocation error is below 100 of meters. And the completeness magnitude can vary depending on where and when, but it's about 1 to 1.4. So the area that we are, so I will show you just one tiny part of the results that we got with this deployment in this area. And it's the seismicity that is associated with the slow slip event. So here you see in colors, red and yellow, you see the slow slip event that was seen by the GPS. And on top of that, you have the seismicity that is color-coded by time. So here you have the latitude as a function of distance, magnitude as a function of, sorry, it's not distance, it's time, sorry. Magnitude as a function of time, and here it's the GPS. So you see that the GPS is a very poor instrument, basically. I should switch. But with the seismicity, there is quite a lot of interesting things to look at. So first of all, the geodetic magnitude is 6.6, as I said. So there is quite a lot of seismicity, but this seismicity accounts for a very, very small part of the geodetic magnitude that was released, because it's mostly aseismic, okay? Still, the seismicity can provide us with some nice details about the dynamics of the slow slip event. So one thing that we can do first is to look at the distance in between events. So here, please look at the blue line. So when we compute the distance, the number of pairs with a distance lower than a given value here, we see that it's following this line. And this gives us two extreme values between 5 kilometers and about 40 meters. So 5 kilometers refers to the area that we are looking at, and 40 meters gives us more or less the uncertainty of localization. And then, if we look at the dynamics of the seismicity, we see quite a lot of things in the seismicity. So we see that the slow slip event starts about here. So it starts slowly and then it accelerates. There is quite a lot of seismicity associated with this. So it starts here. Then there is a first cluster that is very swarm-like. Then there is a quiescence here for a couple of days, 5 days. Then there is a larger earthquake about magnitude, 5.3. And then from that earthquake, we start to have a bilateral propagation of the seismicity, which corresponds to the bilateral propagation of the slow slip event as well. So, yeah, this is pretty nice. And then if we look, if we zoom on the initiation phase, we can look at the detail of the seismicity swarms associated with the initiation. And during this initiation phase, we see that, okay, we have a first cluster, then the second cluster that is very swarm-like, then a third one, and then a fourth one. So if we look at a cross-section here, so look at the scale, so we see that the seismicity is mostly on the interface, but we see small splay faults here that are activated by very small earthquakes. So this looks like splay fracture that are propagating in the overriding plate. Then if we look into even further details at the dynamics of those different swarms, so we can look at this swarm, the swarm number 2, that is very swarm-like. And if we do a cross-section here, like this, on this swarm, we can have here, so here it's a cross-section, and here it's the distance along the, it's color-coded by the distance along the profile. So on the right it's in red, and on the left it's in blue. And what you can see from this cross-section is that the seismicity during this swarm really ruptures small fractures that are disconnected from each other. So you have, first of all, you see large-scale propagation with faster propagation rates. So you have dual migration rates. And what is interesting is that those fastly propagating asperities are really disconnected from each other. So we can interpret this as really a fault with patches and asperities that are disconnected from each other, and that is associated with also a diffusion of fluids along the swarm. Then this swarm here really starts with a main shock, and when you look at the Gutenberg-Richter at the magnitude frequency evolution, so you see that it's really like a main shock and aftershock. So you have swarm, swarm, main shock, aftershock, and from this main shock, aftershock, you start to have really the bilateral extension. Okay, so it's really interesting because this area, sorry, I forgot to mention that obviously this initiation phase is really close to the seamount that was inferred from gravity. So it's interesting because we have a shallow slow slip event. It was never seen in Chile, but obviously it was seen in other places like New Zealand. And so here it's a figure by Shadox and Schwartz, where they show that they have a slow slip event associated with a lot of swarm seismicity next to a subducted seamount. So this is probably very interactive. You have an interaction between the seamount and the roughness of the subducted seafloor and fluids that generate this swarm seismicity. And yeah, moving fast. What is also interesting in this area is that you have a lot of swarm seismicity. So Yannis revisited several swarm sequences using the catalog that he had, but also catalog that were done using permanent stations. And he also revisited a catalog by CSN and USGS. And he sees that there are a lot of swarms, that there were a lot of swarms in the past. So if you look at the swarms that were relocated with the same velocity model, etc., you can compare the location of those past swarms. So in 2023, we have the blue dots. It is what we just have seen. And we have past swarms with different colors. What is interesting is that in the area of the initiation, it's an area that has been associated with a lot of seismicity during the past swarms also. So it seems that this location of the seismicity is really persistent in time. And so it seems that it's really structurally controlled. And here we have the arrest of the 2003 slow slip event. And I'm done. Interestingly, it's an area where we start to have a seismic behavior towards the south. So the reproduction of this seismicity really shows that there is a persistent segmentation and structural control on the seismicity and the slow slip event. So here is a wrap-up slide with the macroscopic features, the fact that seismicity highlights the dynamics of the slow slip event, and also the fact that it's associated with fluids. And then asperities are persistent and structurally controlled over the years. Thank you.
Yoshi, you have a question? We have time maybe for 2 quick questions. Any questions from students or postdocs first? Or maybe? No questions? Yoshi?
Very nice results. Can you comment on the historical seismic slip events in this region, whether it is repeating in a similar fashion, starting from similar initiation locations, or do you have evidence of,
In fact, okay. So this area was poorly instrumented, so there were not a lot of GPS stations. So the only slow slip events that were recognized in the area were deep slow slip events. Okay. So 2 of them were seen so far and well instrumented, let's say. The shallow slow slip events were not seen so far with GPS because it's offshore. So we need, offshore data. Yeah. But if you have a lot of GPS, then you can find the tiny signal. What is interesting is that there were regular swarms. Right. So because we have a lot of swarm seismicity associated with the slow slip event, we can infer that there were past slow slip events that we could not monitor with the GPS. And so we infer that those past swarms were probably associated with slow slip in the area. Mm-hmm.
Which is undetectable, you're saying?
I mean, it's, we suppose that swarms are associated with slow slip
Because
events.
in New Zealand, shallow slow slip events, doesn't necessarily repeat from the same initiation. It's kind of chaotic in terms of initiation point. Overall, the slow slip happens in a similar area, but the initiation, I don't think it's necessarily comes from the same location.
don't say that it's necessarily initiation. What I say is that what we here is the initiation of 2023, and it's an area that was seismically active also during the past swarms. So for example, in 2006, there was a swarm that was further north, so probably associated with a slow slip further north. And it was also associated with some seismicity here. I don't show it here because the problem is that it's also, the location. So it was it was this one. So it was associated with a lot of seismicity. But the location is not very clear for that one. Yeah.
So I think Nakaro-san also has a question. Please, if you want to say.
Okay. Question, but you mentioned that slow seismicity occurred in the disconnected distribution there. So, do you have some information about the focal mechanism type or
We have not computed the focal mechanism. It's a very small seismicity, so we'll try to compute focal mechanisms associated with those smaller quakes. But so far we have no clue.
The emergence of some kind of oblique.
Yeah, I mean it's very interesting because it's really like a shear zone. Okay, you have like a large-scale propagation, and during this large-scale propagation, you really see individual streaks that are disconnected, where you have very fast propagation. So it's pretty neat. Yeah.
Okay, we're squeezing one more question.
Okay, yeah, because given that explanation, why are you invoking fluids rather than just a difference in materials around the seamount?
I mean, we can discuss. No, I'm invoking fluids because, I mean, it's swarm-like behavior, okay? Because we also see splay fractures that are activated during this swarm-like behavior. So it looks really like over-pressurized fluids. Also, there were, like simulations that were showing that when you have like dual migration, it can be associated with a fault infiltrated by fluids and with asperities. So the asperities explain, like the fast migration, and the fluids explain the slower diffusion. But we can discuss, obviously.
Okay, so thank you, Anne, for a great talk. And our next speaker is Lingsen. He is talking about the geometric ruptures of the Noto.
Hello? People hear me? Okay, great. All right, thank you for having me. I'm Lingsen Meng from UCLA. So Kato-san yesterday already introduced this Noto earthquake in this year. So I think I'm probably going to focus more on the coseismic parts of the earthquake. So this is a collaborative work between myself, a very capable grad student, Liu Weixu, Chen Ji from UCSB, Pablo Ampuro, who's an organizer here, and collaborators. So most of what I'm showing today is published recently in this paper on Science. Okay, so this is the New Year's earthquake this year on the Noto Peninsula. So as Kato-san already said, the tectonic setting here is that it used to be area 1 through extension, and then recently about like a couple of million years ago, it started to underwent compression. So this is a rare event. We are having a kind of offshore thrust event, but you have a peninsula on top of it, so you have pretty good near-field observations. So some cool pictures Carlos also showed. There's a big coseismic uplift. This is 4 meters you can measure at the shore. And this is a satellite radar images. You could do cross correlations before and after. And it actually shows, if you zoom in here, you can see there's about 200 meters new shoreline being created by the earthquake. So, we do these back projections. This has been done now routinely for large earthquakes. And for this particular earthquakes, we're using 3 arrays stations in Alaska, continental United States, and also in Australia. So, if you want to know more about this, there's going to be a tutorial this afternoon to, just to run my code. I use this for my graduate classes, so should be of interest to some people. Anyway, so this sees the bilateral kind of rupture propagations pretty clearly, and these arrays are sort of complementary to each other. So some sees the northwest propagation better, some sees the southwest better. Now this is the distance versus time plot. You see a lot for dynamic rupture simulations. So these are the two branches going to northeast and southwest. The initiation parts, which Kato-san also says, citing the my paper, was somewhat slow, with a speed of about 0.8 kilometer per second. So I don't think this teleseismic back projection has that resolution to examine the detail in very early stage. And this part, I think this is more of a early stage of a bilateral rupture propagations, and if you don't have the resolution, you're just seeing one, you're seeing a skewed propagation towards a dominant direction. So I wouldn't say like the rupture speed is that slow. Anyway, so we also done finite fault inversions, kinematic finite fault inversions for this earthquake. And as I was saying, this is an earthquake has fantastic near field and far field seismic recordings, and also GPS, and also SAR images. So you can do a really good job with it. So I think this is the displacement from ALOS, and this is the GPS and our fitting. So you have some very good stations right above the peninsula. And this is the geometry of that three segment of faulting we put in here. Now, this is the coseismic distribution for the three fault segments. So while overall the segment 1 has a lot of sleep with maximum around 10 meters, and the segment 2 has a little bit less, and segment 3 has the least. So now what's really interesting is this initiation parts of the earthquake. So the colors here shows the sleep, and the contours is the rupture time or the breaking time at individual parts on the fault. So so you can see some cool features right here. That this is the hypocenter, and see that the northeast, the propagation is a bit slow, so the contour is dense. And it's also sort of slow right here, around 10 seconds. But something happens at this 10 to 12 seconds where you see this big advance of this 12 seconds contour. Now, just for the sake of time, I'm going to go to the interpretation here. So I think what happens here is, as shown by this schematic here, we have sort of a due initiation process, which means that you have this initial hypocenters and just doing its thing, propagating, but the progress is kind of slow because there was a barrier near this A2 zone where it has large sleep, but also slow rupture speed before the second break. However, there was a sort of a second initiation, hypocenter 2 that we are referring, that's breaking around 10 seconds. And the result is that it's kind of unzipping this area, this barrier from both sides, so that it becomes a lot easier. So you imagine you have a sticker on your table, and rather than zipping it from one end, you are zipping it from both sides. So that sort of accelerated the process. Yeah, so that's the essential part of the results. So we actually also went through to see that if we can see some waveform signatures, and Kato-san also showed this, like this is the acceleration being integrated into displacement in the near field strong motion data. There's lots of things, but if we just look at, this is the raw seismograms and its envelope. So if we just look at this T2 marker, that's the S wave from the breaking of the A2 area from the second, from the big asperity. And we sort of think that the beginning of this wave train here should be the part where you have that second hypocenter. And we sort of locate that based on the near field stations beyond the phases we're picking, and it's right here. So it's like within this big pocket of this 12 seconds contour. Okay, so we are also checking how consistent our observations are. So these dots are from back projections, and these colors are from the maximum sleep rate from the finite fault inversion. So you can see they're doing a pretty good job matching each other overall. So the moment release before the breaking of the second hypocenter, just the first 10 seconds from the first hypocenter is about 6.4, and then the second asperity alone, if you consider it's a sub-event, is about 6.8, right? So I think this mechanism is really important. So without this second hypocenter, maybe the earthquake wouldn't grow this big, right? Because this second asperity created a lot of momentum for the earthquake to keep expanding. So its relation between the swarms and the main shock, we know this is an earthquake has a lot of swarm, there's a fluid involved. So like Kato-san also says that like the earthquake is sort of, it has a lot of swarm activity, but the earthquake is kind of small before 2020. But now, then after 2020, between 2021 to 2024, there's lots of bigger events, right? It's some sort of a different mechanism or different structural control involved. This is for, if you just divide these seismicities into 4 clusters geographically, and these are the deeper area, and this is a shallower area. And this A2, the area that we created the second sub-event, seems to be right at the edges of these swarms. And the swarms is kind of migrated, so this is color is time away from the main shock. So you have events start from here, the S group, and it's migrate to W group. And then because it hits this barrier, it couldn't go there anymore. So it's migrated laterally to N and E. Okay, and it seems like this swarm areas somehow enabled the main shock hypocenter to break, but this barrier is probably places of very low permeabilities, so that these fluid involved seismicity did not penetrate it until the main shock occurred. So yeah, so I'll keep this short so that we have more time for the next talk and the lunch. So just go to some thoughts, food for thoughts. So I think this is a very good example where we see there's a fluid field, porous fault, and I wonder like if we could do more surveys like magnetotelluric or tomographies to investigate the role of fluid migrations, just like what Andreas and Anne was showing over there. So studies of earthquake predictability is also what I think Yoshi was talking about yesterday. I think like people are now trying to do this predictions, making some progress with lab experiments. But you know, you can see earthquakes are complicated. So eventually, if we want to get the right magnitude, it's probably also need to looking into how earthquake can grow, can propagate and arrest. That's also important. Now, there are also many other swarm activities with fluid involvement, such as the Kahula swarms in California, which has a very similar patterns of exhumed clear migration patterns with diffusion. Like Zach Ross at Caltech, they also identified low permeability in the fault zones. And there's also up-deep swarm migrations. But that one, the swarm somehow circumvented the barrier and keep migrated without causing a big break. So there's more to study in these type of problems. So with that, I'll stop right here and take questions.
Interesting talk. Let's start from, let's do, I think you guys were.
Thank you for your talk. And I think the 0.79 kilometer per second for
Right.
the front speed per stage is too low for the usual rupture speed.
Exactly.
Constrain some. Did you constrain the rupture speed for the finite fault inversion?
Well, actually, no. The back projection is independent of the finite fault inversions. But as I was saying, the initiation, as you could see, this is really complicated. And from teleseismic data, you can only see so much. So and it cannot even see the two front, not to mention the two hypocenter propagations. So everything was just seen as a blurry single front. And it can only see this overall southwest migrations, and without seeing all these delays, dual initiations, everything like that. So I'm just saying that you need to take some precautions when interpreting those.
Thanks for great talk. And I was just curious if the breakup barrier can be seen by finite fault inversion, or is it impossible?
Oh, well, it is being seen by the finite fault inversion. So
was it the rectangles, the diamonds are from back projection?
Oh, the diamonds are from the these different symbols all from back projections. So like this interpretation is mainly based on the finite fault inversion, and also the wave change we can see from near field data. So the back projections, unfortunately, does not help much in this initiation stage. So it's really a detailed interpretation based on the rupture contours here in the finite fault.
I know Yoshi has a question. Roman, the last one.
So it has become clear that from the published finite fault inversion model, Noto, that the assumption about the geometry is so critical.
Yes.
So have you tried different geometry?
Yes.
And what's the impact of that to your conclusions?
Not much for this area. I wouldn't say much, but there is the geometry is very difficult to constrain. So what we did is like we just try to feed planar faults with as fewer segments as possible based on the aftershock, and then you have to fine tune it in order to fit the geodetic data. So, but I think this part of the data is not going to be very sensitive to the geodesy. It's more of the timing and the amount of sleep. So this is more of a strong motion thing. Yeah. You disagree?
I had a question very similar to Yoshi's
but I'm also curious about this geodetic rupture. So how well constrained this behavior based on your?
Well, I think it's like it looks like things are not random, right? So these contours versus the amount of sleep, they are being very nicely outlined. And also, if we simply use these move outs from strong motions, and then you can locate this second hypocenter inside of this contour. And also, like, you know, the GMA has the foreshocks, right? So it's, people know that this is sort of like a two-stage process. So I think that's.
So did you try to using another rupture velocity?
It's not being constrained. The rupture speed is not being constrained here.
If you choose another velocity propagation,
Uh-huh.
you see the similar result?
Well, there's a range of rupture speed being constrained, but it's the absolute value, we don't enforce like a particular rupture speed.
Thank you, Lingsen, for a very active discussion. So our next speaker, which is also the last speaker,
Give me
is
this.
Diana, and she's talking about short-lived and voluminous fluid flow. I know we really talked about fluid, so there's some more evidence from, I guess, geological studies.
Okay. Thank you very much for the introduction. And yeah, again, my name is Diana Mindalova. I'm working in Japan. Thank you very much for this opportunity to be here and have my talk. So I will bring you to micrometer, millimeter scale world. I hope I will provide small, high-resolution piece of a puzzle we're all trying to solve here. And if you want to know more, you can check the paper in Geophysical Research Letters for details. And my co-authors and collaborators are Masaoki Uno and Ryoshi Tsuchiya from Tohoku University, Japan. So, very simple question, how much fluids we have and how big magnitude can be which triggered by this fluid infiltration. And I'm metamorphic petrologist doing some thermodynamic modeling stuff. So I will try to explain most important part and skip the details. So you can see on this picture, it's called reaction zones in rocks. What is it? It's just fracture which reacts with fluids, and during this reaction you will see the hydrous minerals, these dark colored minerals here precipitating. So it's an evidence of fluid infiltration in rocks, okay? And by analyzing these fractures, you can have many useful parameters, such as duration of fluid infiltration, fluid pressure gradients, numerically, and permeabilities. And if you have all of them, we published them in 2020, you can calculate fluid fluxes, and finally, using Magar equation introduced yesterday, have magnitudes and moments of possible seismic events. So I will talk about relationship between fluids and seismic events detected by some geological evidence. And yeah, this talk has 3 parts. Most important and exciting is the third one, so if you wake up during third part, I will be happy, and you can just skip the 2 parts. And rocks we are analyzing, surprisingly, coming from East Antarctica, and there is reason for it. Maybe I will have question or not, I'm not sure, but why East Antarctica? Because rocks here are very dry. We don't have any weak minerals which has water in it, which can give you the weakening. So it's basically dry rocks. And we can detect single or the first fluid infiltration here, so I hope you will all agree that it's fluids working there. And how it looks in the outcrop, so we just need these reaction zones in rocks, which cuts through the very dry host rock or surrounding rock, so there is no water there, and in the reaction zone we have some fluids which are in the form of hydrous minerals, which it's minerals which has water in it, so it's basically fluids. Okay, so this is how it looks in rocks, and we make thin section, and it's like thin rocks, chips, and analyze them by geochemical analysis. And also important point is we have apatite which have high chlorine content, and our idea is this apatite will precipitate directly from fluids infiltration. So you have fluids coming, and some mineral will precipitate from it. So the change in chemistry will help you to have the time scales. And our biggest problem as geologists to know the time scale. You see some deformation, but you never know. It takes millions of years or seconds. So this mineral is very useful to have short time scales. And just how to have fluid infiltration timescales from our analysis, you can see the chlorine contact measured in apatite here, and it's changed with distance from the fracture. So we fit it to the reactive transport model for local equilibrium. I will skip the details, but it gives you advection and diffusion part, and in our case, this fluid flow were dominated by advection, not diffusion. And if it's dominated by advection, you can have shorter time scales, and our time scales is tens of hours, which are similar to the short slip events. So another one I think it's important to introduce is fault valve model. Many people discussing here, but maybe not all seismologists familiar with it. It's basically discuss that rise of fluid pressure can fracture rocks and create fluid pathways, but these pathways will be sealed with time. So it's periodic cycle which happening, and it's useful to explain earthquakes. But there is no numerical constraints of fluctuation, because you need fluctuation. Single permeability cannot explain the whole cycle. So what we did, I will speed up a little bit. We provide a methodology to estimate this permeability fluctuation and fluid pressure fluctuation in rocks. Yes. So usually people just assume lithostatic to hydrostatic fluid pressure gradient, but here we provide the numerical estimation. And we use thermodynamic modeling for this. If you have questions, maybe we can discuss later, but it just uses Gibbs energy minimization to give you activity, and this activity can be recalculated into fluid pressure. And yeah, this is the method, and the stages we could detect it with it. So here you can see the permeability fluctuation. We start from very low permeable host rock, and then permeability going up, we have a fracture. So after that, it's going down again, and you have sealing stage. And also fluid pressure, we do the same. We calculated numerically fluid pressure to explain this mechanism. And we have time scales, tens of hours. So yeah, it's fault valve model here. And then finally, we can estimate fluid flux. So to estimate this time-integrated fluid flux, you need time scales and permeabilities, and we already have them. So the last part left is how much fluids come through our fracture. And I use two methods. Just to short my talk, they have similar results which overlaps. I use two just to check myself. So this equation have time scale and permeability of fracture and fluid pressure gradients with viscosity coming from literature, and the fluid, permeability of the fracture coming from the fracture weights. So it's cubic law. And another method I'm just skip, but it's thermodynamic modeling. I use this method to check myself, and it's just basically based on how much silica or any other elements will move with fluids. So it can give you the fluid flux as a result. Maybe you know, like there are often silica veins finding in the faults, and only silica precipitates, so that's why it's very useful to use silica. And it has high solubility, so it will move with changing in temperature and pressure, and it can give you the fluid flux. And last part, which is most interesting, why we need all of this. So again, I spent maybe 5 years to have all these parameters from single rock. It's not easy, but at least, yes, these parameters all constrained by geochemical modeling, and I think it's okay to use them for further calculations. So here you can see the logarithm of time-integrated fluid flux, and it's changed from 10 to 3 to 10 to 6, power 6. And if you have this time-integrated fluids timescale here, then you just use geometry of fracture, size of fracture and length of fracture. Maybe with solving scaling problem, you can have wider folds. Here we're just discussing tens of meters, but yeah, you can use it in other location. And our fluid volume resulting from this time-integrated fluid flux is 10(1 to 10 power 4 cubic meter. And then we use Magar equation, seen here, so you need shear modulus and fluid volume to have seismic moment, which can be converted to the cumulative magnitude, so it's maximum, we expect, okay. And we compare this with fluid injection experiments here. So we have slightly lower fluid volumes coming in our case, and x-axis is fluid volume. This is, I believe, a seismic moment and magnitudes. Okay, so we finally have our volumes and we have our magnitudes. So, and we have time scale, which is very important if you want to discuss relation to seismic events. And we plotted and compared to slow slip events. Here, scaling laws, people discussing it, I don't know. I just believe what I see. So regular earthquakes here and slow slip events here, and our studies come here. So y-axis is duration of the events, and on top you can see the magnitude and seismic moment. We are still close to slow slip scaling law, but it was updated in 2023, so we have hidden zone. And what is really amazing, I think, is that geology can give you the hidden data in the region you cannot detect by geodetic measurement. So geology is a powerful tool. Please don't forget about it. We have different hydrous minerals which are useful. Yes, and so my last slide will be how much fluid we have, that much, and how big cumulative magnitude can be 1.96 to 3.8. So it's low, yeah. But it's just single event, and I'm looking forward to have more and plot them on the previous map to prove this method can actually work. Thank you very much, and I'm open for questions. Okay.
So one about, you started to name your talk as all in one structure. So this much fluid is transmitted to a single structure that you studied?
Yes.
Okay.
Yes.
And
it's still powerful.
On the time scale of what? So that's the first question. And the second question, so you show these events that are in this zone that is hidden, but these are not the actual events, right? These are what you would think the events, the magnitude would have been, right? Based on the Magar conversion of the volume, fluid volume, to potential event input course. Or you studied the actual, these are the actual events that have been corroborated, the slow sleep or seismic, whatever.
It's what I want to do, right? So it's not only fluid volume converted without any evidence of seismicity or shear displacement here. From rocks we can see some shear displacement, and I have some shear displacement which is continuous along fracture. So
this is a displacement on your opening wall structure?
Yes, and it's not opening but shear, yes.
But it's a fracture that permeated fluid and being sealed off and has
Yes.
finite opening that we talked about for permeability.
Yes, yes. But the reason why I'm here, because I really want to compare it to the region which has seismic data in real time. Antarctica, there's not so many seismic data we can work with, so I want to compare and see how is the relationship with real time data. it's very important. I agree with your comment.
So what was the time scale for this 10 to the 3 cubic meters flow for refraction?
Oh, the minimum is like 6 hours, maximum is 70 hours. So we analyzed several samples and tens of hours, yeah.